1, 2, 3 test.
That should be able to pick that up. It might not be very loud in the room, but
You want to use your
SciPy.
SciPy.
1, 2, 3 test. Romans, fellows, countrymen, lend me your ear. Can you hear that?
if you guys have any questions or need anything, or you're just ready to rock?
Yeah, I think I'm. Just connect this keyboard in case we need it.
Meanwhile, guys, could you make sure
I'm gonna go check on any of the rooms.
That it works?
So visibility back there. Is this good?
One thing that has been helping people with the projectors is changing to light mode.
From dark to light.
I see. So is that better on light mode? Where is it? Preferences, profiles, oh, theme. Color theme. Is this better? Dark better or light better?
All right, if you're all set up, I'm gonna go check out your neighbors. 318.
Shall we start?
Go for it.
Recording, micro, everything? Everything running?
All right. If anyone has any installation issues, just raise it.
It's doing something. Should it be doing more?
Could you extend this? Or no?
Well, it's.
No. All right.
I think I'm just going to speak closer to it. All right, so welcome to this joint tutorial with tsbootstrap and sktime, workshop brought to you by both packages in a friendly collaboration. With me today here is Sankalp Gilda from tsbootstrap. My name is Franz Kirai. I'm one of the core developers of sktime. Today we're going to look at a tutorial on bootstrapping, probabilistic modeling, probabilistic predictions in particular, with a general introduction to sktime and tsbootstrap included, but also homing in on a few cutting-edge, bleeding-edge features that we have been developing together around probabilistic forecasting, probabilistic prediction. So we're going to see probabilistic forecast types, probabilistic forecast evaluation, time series bootstrapped, and also reduction to tabular regression and tabular probabilistic regression. All the notebooks are available on Sankalp's GitHub, so you should be able to see them in the public repository here. That's the repository that was also shared beforehand. So you can clone the repository if you want, or follow the repository instructions in the README. So in the README, there are instructions on how you can set up the notebooks locally. So that might be helpful later because there's a few exercises, or you may want to play around with the code. There's also a binder link that should hopefully work. So we noticed there was a broken link, unfortunately. So if you notice binder not properly working as it should, then please let us know immediately. Generally, this is meant to be a very interactive workshop today. So we have 4 hours. So if you have any questions, please feel free just to raise your hand and interrupt. and one of us will be speaking, the other person will be running around and trying to see what you're doing, trying to, and if you have any questions, raise your hand like this, and that person.
Only about an hour and a half ago, I pushed a new version of tsbootstrap. So even if you installed it previously, I would recommend you to update it. I caught a bug, and then I just pushed it back.
Yeah, I'm not sure if this is on the microphone in the stream, so I'm just going to repeat this. Sankalp just said, about an hour ago, we pushed a new version of tsbootstrap. So if you've installed already previously, there was a bug that impacts the notebook, so you may want to just install the newest version of tsbootstrap. I suppose we both have to speak into this microphone or it will not be heard. All right, so quick introduction. sktime, tsbootstrap, both Python libraries. sktime is a Python library for machine learning with time series learning tasks specified broadly. tsbootstrap is a library for time series bootstrapping. Both libraries in their design philosophy are inspired heavily by scikit-learn, so unified interface for objects and estimators with a modular design following the strategy pattern. So objects of the same type are exchangeable, they follow exactly the same interface. For instance, you can pick bootstrap algorithm 1, and wherever it fits as a component, you can pick bootstrap algorithm 2 instead. Both libraries are composable. You can build pipelines, you can build composites, we will see them today, and they offer a simple specification language and a parameter interface, set params, get params. You might know it from scikit-learn already. There's also a very active community behind sktime and affiliated packages like tsbootstrap. So we're striving for ecosystem integration, multiple packages working together, packages becoming more interoperable, and we aim also to provide decentralized open governance for collections of algorithms and collections of packages. The community is welcoming, it's open. sktime has numerous mentoring opportunities, especially for junior data scientists. We're a neutral, non-profit, openly governed organization, and the software is released under permissive license for broad use. If you want to get involved, if you like what you see, you can check out the sktime new contributors guide. tsbootstrap also has one. There's an sktime Discord, so with tsbootstrap, currently we also collaborate through the sktime Discord, just because bundling efforts and contributors make sense in this case. You can follow us on LinkedIn as well, where we have announcements of workshops, which may also be online, or version releases. Okay, before we start, I've been talking about the scikit-learn unified interface, the scikit-learn style unified interface, the philosophy behind sktime tsbootstrap, quickly explaining what it is. If you have not used sklearn before, can you raise your hand if you have used sklearn before? So you raised your hand before you knew whether I was saying not or yes. Okay, so can you raise your hand? Okay, that was a true statement. Can you raise your hand if you have used sklearn before? So that's about half, which means it's good if I explain the mother package of unified interfaces. And historically, you have, of course, Veka, or scikit-learn is the first such package in Python. And the idea is each algorithm of a certain type follows a specific conceptual model. So supervised classifiers, supervised regressors, maybe the most common types of machine learning estimators. So I'll explain it for the example of a supervised classifier here. The conceptual model for a supervised classifier is you have training data that you fit the algorithm to. So you ingest data, in this case, you observe features, so yellowness and roundness, and a label, what is the object. That is ingested in the algorithm. So imagine a Python object. That's a Python object that we're talking about. So it ingests data. It sees data in the fitting method. It mutates its state internally. Then the model is fitted. And then based on this fitted state, with the prediction method, in this case, if you ask the algorithm, okay, my object is now very yellow and very, very round, what could it be? It uses the internal state to make that prediction. So in forecasting, it works very similar, or for other learning tasks, of course, also more complex or less complex types of tasks or objects. Important is here the conceptual model. You have the where you have the data ingestion or the application steps. And what's also very important, you have the concept of a parametric object. If you know what a data class is, it's very similar to a data class. The parameters of the object, the init parameters are its parameters in Python. So you have also a specific interface for the parameters of the object, get params, set params. So adding a bit more code here. So what we did in the picture above, we now do in code. This is the standard example from the scikit-learn tutorial. So x, y, this is the iris data set. It's machine learning 101. So x is rows are different measurements of different flowers. Each row is a flower. Columns are the different types of measurements, so length of the flower petal or the sepal, which can be long or wide. And based on that, you want to infer what kind of flower it is. So that's in the Y. So there's 3 types. They're mapped here. So onto numbers, versicolor or whatnot. So the algorithm trains on the train X and the train Y, and on the test X we want to predict a Y. How does it look in code? So with a support vector classifier here, we create the algorithm and it has parameters, regularization parameters, gamma and C. That's now the instance of the algorithm. It hasn't seen any data, so it's important to note here the parameters are already there before you have constructed your model even. Before you have ingested any data. So at construction of the model, you give it the parameters, but no data yet. That's very important because that's what makes the architecture very composable, which we will see later. So here you have the algorithm constructed. Then we ingest the data. So CLF is now a Python object, an instance of the SVC class. Internally, it fits the model, so it writes attributes to itself, and then you can use it in this fitted state to make predictions, and these are the predicted what kind of flower it is for the X test. Unified interface means CLF could have been any other classifier, so any other algorithm of the same type from scikit-learn. So instead, we could have used a random forest. The rest is the same. And because only specification changes, not application, not ingestion, not inference, it makes it a very flexible interface for algorithms. So you can imagine you have a library of 100 algorithms, and they're exchangeably usable. So you can combine them, compose them in any way. If you invent a new algorithm, you can add it easily. That's one of the guiding principles in object-oriented design. It's called the strategy pattern. You've heard it before. Otherwise, you can think about it as exchangeable plug-and-play or Lego-like composition principle. So that's the unified API architectural principle here, again in one slide. How it maps on the object, the conceptual model. Parameter inspection, get params, set params. That's going to be important later if you want to tune parameters. If you want to take an algorithm and select its parameters, say to be more performant on your learning task. Each algorithm has these parameters that you set at initialization. So you see here, for instance, for the random forest, you have n estimators. So the n estimators here is set to 100, and there's a load of other parameters specific to the algorithm mostly, which you can then set and tune later on, say in an AutoML fashion. sktime, same principle but for time series analysis. So you have multiple types of learning tasks, multiple types of objects. The time series space is richer in the sense that you have a proliferation of learning tasks depending on what you do. Do you want to predict in time, forecast in time? Do you want to classify time series as objects? Do you want to automatically annotate the time series with this is an anomaly or this is an interesting segment here? sktime aims to provide unified interfaces for a range of tasks in the same library, which also makes it useful for composition and reduction. For instance, if you want to do something like, okay, I take a regressor, time series regressor, and I use it now to make a forecast by using the regressor in a time-shifted manner, or I want to combine time series transformations as pre-processing, deseasonalization, or detrending with a forecaster. That's all made easy by consistent choice of interfaces, so unified interfaces for each of these objects, but also a compositionality through a high-level unified interface to which all of these objects share. And all of these are equally extensible, so you can actually click the link here in the notebook and you get to the API reference and an extension template. I think this may have to be a little bit updated because there's actually more tutorials and references already in existence. How does it look for forecasting? The main learning task we look at today, so very, very similar to scikit-learn. This is the base vignette for forecasting. What's forecasting? We have time series, so that's a sequence of values in time, so indexed typically with a timestamp or simply with an integer. We want to continue it into the future by some in some plausible way. How we do this is the same, so we specify the data in a unified format. One difference is we need to tell the algorithm where to forecast to, so there's no x in general. There could be, but there's no x in general observed at the same time points that we want to forecast to. We just want to tell the algorithm, please forecast, in this case, 36 months, for instance, into the future. That's the FH, that's the forecasting horizon argument. Here you have model specification, exactly like sklearn. You construct an object, in this case the naive forecaster, with a seasonal periodicity of 12. You can, of course, look up the naive forecaster in the documentation, what these parameters mean. Then you fit it to the data and then you make a prediction. That's a very, very basic vignette. The forecasting horizon can be passed in fit or predict. Some algorithms need it already in fit, but you can also choose it for algorithms that do not need it to pass it in predict. As a visualization, what we're doing here, so we have the blue time series and we forecast it into the future with, so the naive algorithm doesn't capture the trend here. You already see the airline data set that everyone uses to visualize forecasting, of course. 36, so 3 years, which are actually 3 periods in the case, as you can see, into the future. Time series classification is another example of a learning task. We're not going to talk too much about it today, but just to showcase how different learning tasks are handled inside sktime. Time series classification is you have a collection of time series, and these time series are labeled. On an unseen time series, you want to label that time series. So labels apply here to an entire time series. There are, of course, learning tasks where labels apply to parts of time series. And again, the scikit-learn inspired interface here, you specify the training data, so the training series. This follows a specific in-memory format. sktime actually supports multiple in-memory formats for collections of time series here. So you also have to think about how to model it. One way to format is 3D NumPy instances, variables, time points, or you can put it in a pandas multi-index with a pandas data frame with a row multi-index. These are 2 options. Here is a slightly more complicated specification of the algorithm. You already see we're constructing a distance here, so we're constructing a distance for time series, and then a k-neighbors time series classifier with that distance. So the distance slots into the algorithm, which we then fit just like in sklearn, the only difference being the format of the collection of time series here, xtrain and xnew. So here we're using a 3D NumPy format for xtrain, ytrain, and xnew. Otherwise, everything is similar. So that's unified interface. Now we're talking about unified framework. We're also talking about the wider ecosystem of packages that deal with objects like bootstrap algorithms or time series distances or probability distributions, for instance, from SciPy. In the time series ecosystem, if you've worked with time series and not with sktime, or just in anger in production, what you will see, there's a lot of solutions, a lot of packages out there, a lot of great implementations of methods. There are actually also other frameworks. Now, though what you see, a lot of packages have single or few algorithms. They don't have unified interfaces like sktime. And in the case where they do have unified interfaces, an example for that would be darts, another example would be cats. It is not extensible in the sense that you can easily add third-party packages, third-party implementations, integrating with the framework as long as they adhere to the unified interface. So sktime has unified interfaces. It integrates, or it has an ambition to integrate with the wider ecosystem. It has the ambition to be openly and decentrally governed and to be easily extensible in your own, for instance, third-party library, even in a closed source library, or if you have your own package, you can choose to implement some algorithms with an sktime compatible interface and then have it listed on the sktime estimator register. I'll not go into too much detail about that. So if you're interested in how we manage the decentral ecosystem, there's going to be different presentations we will give from sktime at a conference over the summer. Today we're going to focus on probabilistic modeling, probabilistic prediction in particular, using sktime and tsbootstrap. So what follows now is a general introduction to sktime, then a general introduction to tsbootstrap, and then we will look at, in more detail, probabilistic modeling aspects between the two packages and sktime and also other packages. All right, over to you, Sankalp.
Perfect. Thank you. Yep, that should work. There we go. All right. Perfect. Yeah. In this notebook, we'll, as the agenda clearly shows, we'll go over sktime as it relates to forecasting of different types with different types of data, univariate, multivariate, hierarchical forecasting, and very importantly, probabilistic forecasting, which is sort of the crux of this tutorial. Go. We're going to use a typical business use case and not to motivate why probabilistic forecasting is important. sktime is very well written. It automatically contains several common data sets. Here we'll load the shampoo sales data set. Again, if you're familiar with time series, it's one of the go-to simple data sets that you people use. So as we move forward, so far we've just loaded the data set. It goes from 91 to 94. We divide it into a training set and a test set. The idea, obviously, with forecasting is going to be train on the training set and see how well you can forecast. Again, you can do this very quickly using inbuilt sktime utility function. No one said anything, so I'm gonna assume I'm audible, right? I don't have to do this. Okay, all right. sktime has, among several different types of forecasting models, something called AutoArima. So ARIMA is one of the classic statistical forecasting models. AutoArima uses a specific algorithm to automatically find the best parameters of ARIMA.
It's actually from the ARIMA, so integrated
It is,
system.
right.
It's actually a third-party estimator.
That's actually one of the, just a little digression, that's one of the great thing about sktime ecosystem at large. It doesn't always try to reinvent the wheel. If there are better implementations out there, our developers and collaborators work to provide robust adapters, essentially. So for example, this is an adapter to PMD ARIMA. There we go. We've already fitted and plotted. It's decent, but as you can see, we kind of capture the sense, but it's not the best. Obviously, visually inspecting how well a fit is one thing, but if you want to do this algorithmically at scale, you want to use some sort of metric. One metric that in sktime has several metrics. For demonstration purposes, we're using what is called MAPE, mean absolute percentage error. Just a note, this is not always the best metric for time series forecasting determination, but again, for demonstration purposes, it should suffice. So you see output is about 22.6%. We could tell visually we are getting somewhere, but it's kind of not very good. And that is also borne by this particular metric. 22.6 is kind of high error. We will start to work and improve this model. You go down. When it comes to forecasting, typically you can do one of three things. You can do statistical models. We already saw ARIMA. We can try machine learning models. And these are the two machine learning models, i.e. sklearn models. And these are the two demonstrations that we'll show today. But FYI, we don't mention this here, but sktime now has integrated into Hugging Face LLM models. So we can if you want to play with that kind of fitting, you can also just read through the documentation and do that. Here we'll focus on statistical and machine learning. Instead of using AutoArima, now we use AutoETS. Theta forecaster, again, a very standard statistical forecasting method. There we go. Pardon me, there we go. Okay. AutoETS brings the error down from 22 point something percent to, say, 16.5%. Theta forecaster does worse, both visually and borne by our MAPE metric. You can click on the documentation, obviously, but there are 88 different forecasting methods available in sktime. With that very simple demonstration with a couple of statistical methods out of the way, now we move on to what people kind of really want to see in this day and age, machine learning forecasting. So traditional machine learning models, especially with scikit-learn, they expect your input data to be tabular. Time series data, even if you consider a univariate stream, is obviously not tabular. So our job is to properly tabularize this data. We use the terminology reduction for this purpose, and here we show what that looks like. So essentially, you want to take, if you have a data set, X is your, if you have a data set from T1 to whatever, T15 or T20, you sort of take either an expanding window or a moving window, and you start chunking it. If you say, I want to do next step forecasting, and I want to use 10 samples as my X, so T1 through T10 will be the first row, and T11 will be the Y output, and so on and so on. You can just start moving forward. You don't have to do, this is just for explanation purposes, you don't have to do anything by hand. sktime provides utilities for literally all of this. Here we use a particular type of gradient boosting regressor called histogram gradient boosting regressor. We define a window length, like I mentioned, the length of the how many number of features, if you will. Pardon me, there we go. We go ahead. Something interesting happened. Forecast kind of sucked now. It was 26%, we brought it down to 16, and now it's up to 48. Any guesses why, before I tell you? Well, actually, you can just scroll down. Don't scroll down, don't cheat. Any guesses why?
Window size?
Could be, could honestly be. There are, what's that? I can't hear you.
The starting use of the forecasting?
The what of the forecasting?
The strategy.
Oh, the strategy, fantastic, that's it. Window length is sort of a second order effect in this particular instance. What we did is we used a gradient boosting model, which doesn't do so very well with extrapolation. So if we want to use this clearly increasing time series, we got to massage it somehow before feeding it to our time series model, our machine learning model. Next, we do that massaging. Gradient boosting trees, they are not good at extrapolation. They will forecast well within their observed range, but clearly this data set has an increasing trend. What we do is we use the differencer utility from sktime. The idea is to try and stationarize this input time series before feeding it into our machine learning model. And once we get the output, you want to do the inverse operation, so addition, if you will. You don't have to do anything by hand. You literally just call differencer appropriately, and voila, it just gives you the correct output. Think of it as a black box. You can see it's this fit transform, exactly the same thing you're used to with scikit-learn. We compare the original data set with the new data set. That increasing trend is gone. We literally, if you will, multiply using the Dunder method, and we'll see a much better forecast. Suddenly the error goes down to 20%. Yeah. Yeah. Right. Yeah. So the whole thing with what Franz is referring to is, perhaps I skipped past it right here. The original pipeline was called forecaster, and the new pipeline is forecaster with differencer, which is literally the same type. It's a pipeline like forecaster was. So oftentimes this happens when you try to push model into prod. If you write individual methods, you forget to do the inverse. Smart thing is to use pipelines, and this does it for you. This is essentially pipeline building, and this does it for you with a multiplication. Of course, differencer is a ssimple operation. sktime has a whole host of operations, but we picked a simple one for demonstration. This was univariate data. Now we'll move to univariate data with or univariate forecasting with exogenous data. Exogenous data, as the name implies, is essentially related time series that's not the original time series you want to forecast, but has some sort of predictive power. An example would be if you're trying to forecast sales, information about past promotions, future promotions. We'll start with loading exactly the same data set. We'll create fake promotion. We'll use the sales data, add some noise, and some simple transformations. So why the blue one is the original data, and then we've created little peaks to demonstrate the promotions in orange. Again, that was the combined data set. We do the train test split. Same plot as before, but just now split into two. So 4 different colors. Now we want to forecast the future values of sales. We can, for this, obviously use the past values of sales, as we've been doing so far. We've also added the past promotions. And thirdly, promotions are often known, if not always known in the future. The company plans out what promotions they want to do. So we're also we're also sort of simulating that scenario by using, thirdly, the future values of promotions. So this is kind of data leakage, but in some situations it's allowed because you're not leaking the actual data set, you're leaking exogenous variables whose values you know for a fact. It's almost like leaking day of the week, you know? Same thing, we start with AutoArima. Forecast improves. If you recall, when we started with AutoArima, the original error was 23%, and that's down to 15.3%. In this particular case, there is data leakage because this wasn't like real promotional data. We created this by adding noise to the original sales data. So obviously there is some leakage. So this particular forecast is overly optimistic. So we'll remove this future promotional data. Here we go. Yeah. We can use a different model for X than for Y. For sales, if I want to forecast sales, I can use AutoArima model. Promotions, you don't always run promotions, right? They are, by definition, every now and then to keep them special. So you use a model called Croston to account for that intermittency. You really, it's basically, again, create the pipeline. You say forecaster Y is something, forecaster X is something. Here, forecaster Y itself could be a combination of AutoArima with something. So these pipelines can be nested within each other, making the whole code very easy to read, very easy to write. Create our forecaster. We go ahead and fit. Okay. Yep. We forecast, AutoArima for sales and Croston for promotions. These are our forecasts for the original, this plot shows the original sales data and the forecasted sales data. I think what we did here was we missed the true future sales data. So my apologies about that. In your respective cells, you can just go ahead and add it. This kind of brings us to the end of this section with just univariate forecasting. I know I've been kind of going fast because I want to keep space for the next notebooks. But if there are any questions, I'm happy to take like a 30-second break right now. All right, perfect. Multivariate forecasting, where you want to forecast not one time series, but two or more time series. We start by using economic indicators. The cadence here is annually. VAR is a popular, it's vector autoregressive. It's a multivariate, by definition, a multivariate forecasting model. And we simply import it and use it to forecast this time series. So to be clear, the difference between univariate time series with exogenous data is in univariate, the goal is to still forecast just one time series, and everything else is just additional helpful information. Here, the goal is to simultaneously forecast two time series, and we know they're related somehow. We can compare the performance by comparing the outputted table with the original input data. If you want to scroll up, you can go ahead and do that. I think Franz mentioned everything. All forecasters in sktime have tags, which this is to make the output very much human readable. These tags are essentially, they contain the dictionaries which contain properties of the fitted model. In this particular case, it even has the name of who the authors are, who the maintainers are. So, and this keeps getting updated every time you make a contribution to sktime, so people get due credit. The rest is sort of self-explanatory. In this particular example, we'd used a multivariate forecaster for forecasting multivariate time series. What we can do to make things a little more fun, if you wanted to, is to combine univariate forecasters to forecast multivariate time series. ARIMA is a univariate forecaster. We went ahead and, pardon me, yeah, we went ahead and, sorry, where am I? Yeah. Yeah, there we go. If you call ARIMA with a multivariate forecaster, with ARIMA in sktime with multivariate data, pardon me, it automatically applies ARIMA to the different single time series in your multivariate data. Like I said, we can see sktime fits one single ARIMA model per time series. You don't have to chain things by hand. You don't have to do a for loop. You just call it and fit it to a time series data. If it's multivariate, it'll just fit one model per column or per time series. Same thing, you can do get tags, authors ignores, handles missing data is set to true. Yeah. So far, we've covered univariate forecasting with exogenous data, and multivariate forecasting. However, in several scenarios in real life conditions, point forecasting just simply does not suffice. This is when we start moving into the realm of probabilistic forecasting. There's like a whole plethora of literature. It's a very well-developed field in and of itself. Here, we will demonstrate how to do simple probabilistic forecasting using sktime, and this will also serve as motivation for the next notebook, where we focused on a very particular type of tool to improve time series forecasts or probabilistic forecasts called time series bootstrapping. sktime provides several different types of approaches to probabilistic forecasting. Again, we're going to keep using the same data set. Auto EDS, like Auto ARIMA, is an auto version of another very popular statistical time series forecasting method called ETS. We go ahead and fit it just like we have so far. We predict it. If ypred here is simply deterministic forecast. However, ypred int, where we want to get the interval with a given coverage, and coverage by the coverage of 0.95 means a 95% coverage, which means that if we forecast 100 points, 95 of them ideally should contain the true value within the interval forecasted. That is what coverage means. With coverage, there's another quantity which sort of goes along with it. This is just FYI, we'll cover it later, called sharpness, which means you want your error bars or your interval to be as small as possible, but still give you the desired coverage, because hypothetically, you could say the temperature tomorrow is going to be from minus 500 to plus 500, and you could be right, but it's a nonsensical forecast. So you want those intervals to be as small as possible, but still guarantee a given coverage. So these are metrics about regarding time series forecasts. We'll cover them later, but just FYI. Here, we go ahead and predict the actual deterministic forecast, which is a green line, and a 95% interval, which is the green band. There are several different, I mentioned sktime provides several different types of Probabilistic forecasting methods, we used predict interval, which gives you interval forecasts. There are predict quantiles. If you want a predefined quantile, predict variance, which will give you which will forecast the variance. Predict proba will give you the entire probabilistic distribution. As you can imagine, this is the most intensive method, and it uses another library in the backend called skprobe. I won't spend a lot of time going over what's already on the screen. Tags, sktime is full of tags. Another important thing that you can do is filter by tags, literally like Control F. You want to find out those forecasting methods which allow a certain type of forecasting. So if you want to forecast intervals, you select by capability and you say predint is true, and it will only list those which fulfill this condition. So we have 48. If you recall earlier, when we simply output all forecasters present, we got, I think, 87 or 88. Now, when we've used Control F, suddenly we're down to 47. We did predict interval. We can try different methods. We can start with quantiles. So you can predict quantiles, take multiple alpha values. It's not like you have to keep calling this method with a single float number multiple times. So the more numbers you give in here, the more outputs it'll get you. Predict variance gives you the variance in your forecasts. And predict a probabilistic distribution, which it returns a base distribution child instance, as it's mentioned. So if you look at the output, it has a mu and a sigma, because we assumed here that it follows a normal distribution. If you know the data generation process behind your actual data, you can mention that by hand, and skpro will do all the heavy lifting in the back end. There are several probabilistic methods that, again, due to time constraint, we haven't shown here. What's that? Conformal intervals are a very important and sort of a very hot area of research. They've been gaining popularity more and more. sktime has conformal forecasting capability. We can do probabilistic forecasting hierarchically. So let's say if folks are familiar with the M competitions, which are a very popular time series forecasting competitions, they often contain hierarchical data. You can leverage sktime very easily. You can use bootstrapping probabilistic forecasting. Let's say you have your time series data, some black box forecaster, and an output. You can literally create, using bagging forecaster and SEL bootstrap transformer, multiple copies of your input data, keep feeding it into your black box forecaster, and get multiple outputs. You can combine these. You can take this time series bootstrapping capability as part of a sort of a more advanced, say, conformal forecasting algorithm. Just feed it in there, and you'll get better conformal forecasts. Hierarchical forecasting, very important in industry. Here's a motivating example. You have home appliances. Some could be for food preparation versus food preservation. Again, food preparation could be hobs, ovens; preservation, fridges and freezers. We will create a historical monthly sales data set. There we go. Okay, food preparation, food preservation. Everything is a pandas data frame, multi-indexed. Hobs, fridges, etc. As you can see, these are on at a monthly cadence. You want to see the hierarchy. You essentially do a lock or an iLock, and you see Each of these product lines contain the two product groups that we mentioned in the diagram above. You can very clearly visualize the different time series in the hierarchy. So it might take you a little, like a few seconds to actually parse the various plots in here, just because of the fact that they're crowded. But the fact remains that once you load this data set or you provide your own hierarchical data set that's in this format, in this multi-index format, you can very easily plot it for visual confirmation that everything is working. You want to forecast these multiple categories simultaneously, and oftentimes a big challenge with hierarchical forecasts is reconciliation. If I have category A and category B, and if I do future forecasts of them separately, those numbers should add up to future forecasts that I do for the parent category. So this is called reconciliation. In sktime, you don't have to worry about it because it, again, does the heavy lifting in the back end. We are, again, using AutoETS, the same model that we've been using so far. And same thing, fit predict, you change nothing. You mentioned the future time horizon. Y-train is the multi-index data frame that we saw. It takes care of reconciliation on the back end, like I mentioned, and boom, you have your forecasts. Here we use AutoETS for all 4 levels. You can actually use, if you had a reason to believe that you'll benefit by using different forecasters for different time series, you can do that by hand. In this case, since this is a demonstration, we used AutoETS.
Different demand forecasting classifications, for example. I realize it's not hierarchical, right? But so in demand forecasting, where you're grouping 4 different categories, right, 4 different demand classifiers, would that be a scenario where you use this to apply different models based on the demand classification?
Yeah, yeah. Good question.
So do you mean like ADI, CV?
Yes. Yeah. So where you get like lumpy, erratic, smooth.
Yeah.
Exactly. So we recently actually added, and that was very recent because it was on popular demand. So we recently added a transformation tool that for a collection of time series computes which of these 4 classes it is, and you can also select the threshold if you want, or you can use an arbitrary cluster if you're not happy with these 4 classes. And then depending on which it is, we apply different forecaster. So we do it in the specification step. So if you look up ADI CV transformer, it has an example where you do, so you have to combine the transformer, which computes the class, with, and I forgot the name, I think it's by group, forecaster or forecast by group, something like that. So it should be in the composition section of the API reference. I can show you actually. Why it's like that continuous.
After that, actually, I think we would benefit, Franz, if you explain to the group this particular data set and this particular problem. I don't think everyone knows.
Well, hierarchical stuff is not the topic today,
Sure.
but I'm happy to reply to popular demand questions.
Sure.
We have time at the end, or
Absolutely.
I'm still around for tomorrow.
We are nearing the end of the notebook. Here we demonstrate that the same error metric that we've been using with univariate data, univariate with exogenous variables, multivariate, probabilistic forecasting, we can just as easily use these with our hierarchical data. So either you can get one error metric for the entire sort of the parent category, or you can just select raw values as a parameter, and you can get error metrics per category in the leaf nodes, if you will. Again, there are several types of forecasting features. Franz mentioned they just added one that we haven't used here, and there's documentation. Please feel free to explore. So recap. We looked at univariate forecasting using statistical models and the sklearn models that we know and learn. In this case, a simple tree-based model. We work with univariate data with exogenous variables, where the goal is to forecast the future values of one time series using additional information. Multivariate forecasting, where you want to forecast multiple time series future values. And you can do this by using a forecaster that natively handles multivariate data, or you can very easily combine several univariate forecasting models. We looked at probabilistic forecasting, and finally hierarchical forecasting. Important to mention the control F feature, which is enabled by the tags. You can select whatever property you want, essentially, and look at the all estimators parameter or method, and it'll give you what you want. In the next notebook number 3, we move on to tsbootstrap, which is a different library, but is integrated into the sktime ecosystem, which has been created very specifically for bootstrapping time series, which are not IID, and hence you simply can't replace time, sample A with sample B without losing the temporal nature. And then we move on, of course, in notebooks 4 and 5, showing how to do probabilistic forecasting with sktime in a little more detail. Yeah, just credits, this notebook has been presented before. All right.
Quick question maybe, is the size of the letters, is it large enough?
It's readable at the back? Perfect. Okay. I would like to motivate this by using a very real data set. As it says, imagine you're well, you don't have to imagine, I'm sure several of you are data scientists already, but imagine you're a data scientist who's participating in the M4 competition. You want to forecast monthly time series for the next year and a half. You want to provide confidence intervals for your forecasts, because these are sales time series. Depending on what your forecast is, decisions worth millions and hundreds of millions of dollars in real life could be impacted. And you want to assess the impact of different bootstrapping methods on forecasting accuracy. We will quickly look at the M4 dataset, but just overall, it contains 48,000 diverse time series. Each has unique seasonality, trend pattern. The idea here is to use tsbootstrap to show that by bootstrapping each of these individual time series, using the different methods enabled in the library, you can get a whole plethora of solutions. What will you learn by the end of this notebook? You can apply the various bootstrapping techniques from tsbootstrap to diverse time series data. You can generate believable, robust confidence intervals, and you can compare the performance of different bootstrapping methods on forecasting accuracy. Okay. Here, what is time series bootstrapping? It is resampling technique for time-dependent data. So what is regular bootstrapping? It simply means resampling with replacement. It's used for a number of different tasks. We'll actually see what those, with examples, with dummy data, what those tasks are and why bootstrapping is so important. But one thing with bootstrapping is it assumes all your data is IID. Time series data is not IID. Hence, there's a whole family of methods that have been created, that are actively being created for bootstrapping time series data. tsbootstrap brings several of those into a unified package, and it works very well with sktime. Sktime works very well with sklearn, which means tsbootstrap is integrated into the ecosystem. It's important for M4 competition. We are using this as a motivation. It lets you generate confidence intervals, gives you uncertainty, and if you go back in time and participate in this competition, you can make money by winning. Challenges with traditional methods, we've already gone over this. There is autocorrelation in time series data. You do IID bootstrapping, all of that is gone, which means you'll lose, your inference is going to be unbelievable, literally unbelievable. So there is a convertdata.py file. I'm gonna maybe stay here for 30 seconds, for a minute. If you could just literally do like Python convertdata.py, what it'll do is it'll convert this .tsf file into a .pickle file. So specific data set that we're using, it's called M4 monthly dataset. M4 dataset has been resampled at multiple frequencies. We're using a monthly frequency, and I downloaded it from the Monash repository, and it was available in TSF format. So this particular utility module will convert it into a pickle, then we can read it into the pandas data frame. So I'm gonna wait for, it should be fairly quick. I'm gonna wait a minute or two right here. Folks can do this. Let me know when it's done or if it's not done. Yeah. Could you go back to your repository? Yeah, hold on one second.
Maybe the older name thing.
It's right there. It's convert. You see it? Convertdata.py. Yeah. If you guys just do the repository convertdata.py should be right there. And the other root. So
I can see it. There were the errors.
This is not something that we have done before. Oh.
Yeah, I can, when I debug it, it looks like when you try to do split contrast, it's just a single string.
Hold on one second. Let me see.
Do we maybe want to proceed as an as-if?
Hold on one second. Let me see.
Not too much should depend on this one condition.
No, it doesn't, but it would be really nice if folks had it. And it's, unfortunately, I didn't actually encounter this error, so I'm not
What
sure
kind
how.
of data do you need?
What's that?
What kind of data do you need at the end? Maybe we can fix it quickly.
It's just we want a data frame that looks like this. Essentially this.
Oh, okay. Yeah. So how about
Let's try something.
Bear with us, guys. Live debugging is always a pain.
So we want something like this.
you just need to skip the first line?
We tried it.
Which line?
Because I'm looking at it and it's trying to split, pull a date value out, but that first line of the TSF file is a version and a URL. So
So let's do this.
or maybe the TSF file is not right, because it's just got a SHA in there and a size.
Should that first split be a space instead of the colon? Just split the
Did you
line.
try it? Honestly, the weird thing is it worked completely perfectly.
You're trying to split out data streams, right?
Yeah.
So what's your TSF file look like? Because mine is only 3 lines long.
Yeah. Oh.
I'm assuming
Duh.
it's
think I got it. Just using the dummy thing.
What I've done is I've uploaded this to my Google Drive.
How many do you need? How many columns do you need?
No, that's not the issue.
Yeah, but I'm just using a dummy data generator so we can proceed.
Yeah, it just finished.
Yeah, so it's here. Maybe it was a deleted tree. I think I'm
Sorry.
back to that. I'm just gonna check on that.
Here, we can use this dummy data if we need to.
Okay, so what I did was on README for this repo, I just posted a Google Drive link, which has this TSF file.
Or we could use this dummy data.
Or we could use the dummy data.
How long do you need the time series to be?
It's like, I think 400 or so lines.
But each individual.
I just reverted back to it. I just checked out one of the previous revisions.
Huh, I wonder what happened then. I really don't know.
That's weird.
The one from 105
It's 3 lines. It's so weird.
commit messages have large copies of TSL. But now it has all of
Okay. Let's just wait just 1 minute. I think that's a sweet spot. If folks are able to download using the link that I just pasted.
Yeah, or instead we can use this here.
Sure, but just give, if that doesn't work, give me just 1 minute.
And yeah, sure. We don't need to proceed. I'm just giving alternatives.
I'm telling you, live debugging is the worst. And it's public now.
Do you remember what the key for the M4 dataset is for the Monash?
M4_monthly_dataset.
So this would be M4,
I think by
M4.
the time you're done, folks will be able to download and run the module.
Yep.
Yeah,
Not all the eggs in the same basket. So what
I
is it?
did this whole thing because I didn't want to upload have like a whole separate thing where I upload a pickle file to a drive and folks download. So I uploaded a TSF file, which is within the constraints of GitHub, but now we're essentially doing the same thing.
Hey, what's the string?
M4_monthly_dataset.
Dataset is redundant. And your copilot also thinks that it's redundant. Well, now it's doing something.
The problem if you're downloading, got it. All right. Yeah, I don't think we'll need this anymore. Folks are able to download and convert. Conversion takes about 20 seconds or so. Just hold on 1 second.
It's
Essentially.
always great to have fun together.
You're still what?
I think the conversion on my machine takes longer, but
Okay. Well, it's clear that your machine is at fault.
Yes, we are flawless, okay?
Exactly.
It's your fault. Essentially, the data looks like this. No, this is the dummy data.
So stand-up comedy while we wait.
Franz, that famous German humor, go for it.
Oh. Yeah,
Franz, everyone.
that's German humor.
This is what the data looks like. It has 48,000 time series. 48,000 time series. It should run if you follow the steps up until here, it's run for a couple of folks, which means it's just literally a matter of time. It will run. We go ahead and said we want nice and pretty plots. We set universal matplotlib parameters. And then we start actually visualizing some of the time series from this data set. So there we go.
Is anyone getting the invalid load key thing?
it's just still processing.
Yeah.
It looks like we have the next level. Invalid load key hash.
Did you download for Google Drive? And then you run the module and you get an error?
Yeah, I think it's not ignoring the comments at the top.
How are you running the module? The convert data.py. Literally Python convert data.py.
Are you parsing this manually?
Am I,
I mean, Sankalp.
am I doing what manually?
The convert, is this parsing the TSF manually?
That's what the module does. Okay. Anyways, this is what just a sample of the different time series. These are all sales data. As you can see, they don't have the same starting date, but I just picked a range and plotted five randomly selected time series. Obviously, for demonstration purposes, we'll stick to one time series, which is T1, the blue one, the longest available here. There we go. We just replot T1, and then we separate it into trend, seasonality, and residual. So trend, seasonal, residual. Sales data are famously seasonal, cyclical. That makes forecasting at least partially easy with sales data. We start with bootstrapping. There we go. Wait, Binder doesn't work with Mermaid? It's interesting.
This is my VS Code.
Yeah, again, it works on my laptop. Are folks able to run Mermaid code? Because this was generating a Mermaid diagram.
Do we need an extension maybe?
Extension to what? I didn't add anything to my VS Code. It just worked.
My computer.
Yeah, I understand. I'm saying I don't know what we should add because it just immediately worked on mine. Are folks able to render this or no? The Mermaid diagram? I didn't add anything. That's the thing.
And your copilot edited it when it saw that it was rendering.
Oh, you know what I did? On this laptop, I just installed the same thing I had on my own computer using synced GitHub settings. So maybe it pulled everything automatically without me realizing.
Let's try to install it then.
Let's go. Yeah, I think that should do it. Let's
That
focus on
one?
this. Yeah,
Everything?
just the first two.
Wonderful.
It rendered for me and for a while. And I didn't install.
Do we need to restart it now?
Yeah, it's marked on previewer. That's the one. The first one.
So it's not.
No, try it again. Try running that cell again.
To try to run this, okay? Nope. Restart maybe.
Let's restart.
Oh, but then you have to restart a lot.
No, it's
maybe?
okay. It's very quick. No worries. Go ahead and restart.
Okay.
Oh, just this restart
Oh, this restart.
on the computer.
I thought we were restarting VS Code.
Just, okay, restart VS Code.
I think that's too risky. Let's just proceed like this.
It's risky because
Well, because we risk. Should we have a break, perhaps? How about that? We have been at it for 2 hours.
yeah, something like that. 2
Oh.
hours and 15 minutes.
Well, 1 hour and
Sorry,
15 minutes.
what's that? So you just close the notebook and reopen it? That's it. Just close,
Okay.
close the notebook.
Well, we need to save it first, I think.
No, because you're not changing anything on the markdown. I just closed it.
Okay, so we reopen it now. Where's the mermaid? We should have.
No, no, go up, go up, go up. It's right there.
We should have a break.
Go up.
Oh, there it is. Nice.
There we go.
But we should have a break because we are already, well, maybe not right now.
Let's finish this section and then we can talk about a break. Yeah, guys, so it's just Markdown Preview Mermaid. That was the extension. Yeah, sorry. And this, yeah, sorry, this is kind of on me. I didn't have to install anything by hand because it's synced directly with my other computer. No worries. There we go, okay. Why am I not able to see this? Let me try again. What's happening here?
I would suggest you close the extension window.
There we go. All right, Franz to the rescue. Essentially, this little mermaid diagram shows how we carry out regular bootstrapping, not time series bootstrapping. We're building up to it, and the various things you can do with bootstrapping, the statistical bootstrapping. You can calculate statistics. You can get distribution of statistics. You can figure out how well to trust a model that you fitted by looking at the change of model parameters with multiple fittings, etc. We've covered this, but just a quick recap because we had this whole little thing. Bootstrapping is resampling with replacement. With replacement is extremely important. It does several things. It estimates sample statistics distribution, like mentioned, draws with replacement, and it doesn't, the vanilla IID bootstrapping does not make any distribution assumptions. So here again, I've tried to just demonstrate visually what it looks like. The original time series data was literally numbers 1 through 15, and then these are 3 bootstrapped copies. One constraint that I've imposed with this visualization and in the library itself is the bootstrap copies will be the same length as the original time series copy, original time series data. This doesn't necessarily have to be the case, but it just made life much easier, just coding things wise. But it's very easy to open a PR in tsbootstrap and request changes or make changes yourself. If you pay attention to the 3 different draws, in each of them you'll see repetitions, you'll see things out of order. That's literally by design. That's what bootstrapping is. I've mentioned you can do several things with bootstrapping. You can do model-free non-parametric inference. Again, I'll just speak over the data. Okay, so here, let's say I have I have 2 types of data. One is a simple normal distribution, other is a less simple bimodal distribution, and I want to find what the median is, and I want to have a certain level of confidence in this statistic. So I create bootstrapped copies of the of both respective data sets, and this is done in the code above. If you take a look, the idea here is to show that bootstrapping will get you, if you do given n copies, where n is large enough, you should be able to converge to the original distribution and get a sort of a confidence interval around the statistic of interest. Here I picked median as opposed to mean, because with mean, with a bimodal, the law of large numbers sort of plays a role, and everything converges to one particular number, as opposed to median, where we're actually able to keep we are able to visualize the bimodal nature in the second plot. Had I used mean, this little thing would have also converged to just one number. So on the left, you're seeing what the bootstrapped copies look like. So the median quantity is distributed around the red line, which means the true median is right there, and then there is a distribution around it. Same thing in the right, the true median is the red line, and then there are distributions around it, which the bootstrapping method has produced for us. It can be very importantly in general, and for the sake of this tutorial, it can let you get confidence levels or uncertainty assessments. Again, I won't bore you with the code. You're totally welcome to spend some time at it. Essentially, the idea is, again, here, if you wanted to get a sense of how much can I believe whatever particular statistic, you can create bootstrap copies of the data and calculate that statistic. In this case, the data is synthetic normal data. The statistic of interest is mean, and then we have confidence intervals around it. Then we compare the size of those confidence intervals derived from bootstrapping with the original confidence intervals, and we do pretty well. Model validation, you have data, you fitted a model, you want to know how much should I trust this model? There we go. I'll quickly explain what we did. Again, synthetic normal data, added noise. On the left, added little noise. On the right, added more noise. Tried to find the coefficient of interest, mean. With high noise, we are a little farther away. With low noise, not so much, which again validates the fact that when you try to get the quantity of interest, in this case mean, with high noise data, bootstrapping immediately tells you that there is some noise in the data, and you should believe the dot mean that you get a little less than you would had you had low noise or no noise data. Finally, we can leverage bootstrapping to examine empirical distributions for complex estimators. Again, you can look at the entire code, yada, yada, yada. On the left, we fit a GMM estimator to a bimodal data set. On the right, we fit a KDE estimator. This tells us that bootstrapping is able to, well, immediately we see that KDE doesn't do as well as GMM. The idea here is to simulate complex estimators and tell you that bootstrapping is able to still get you the quantities of interest since it's non-parametric. Vanilla ID bootstrapping simply fits on whatever estimator you give it, and it gives you the parameter of interest. We print out actual values. I'll repeat this again and again in words, and then we'll scroll down and we'll very clearly see why specialized methods for bootstrapping time series data are important and why you just can't use IID data. Oh, pardon me, IID bootstrapping. Here we use, sorry, pardon me, let me scroll up. Dun, 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 dun. There we go. We use another very popular time series data set. It's an oldie and a goldie airline data set. Everyone uses it to demonstrate stuff. We do train test split. It's very important for time series to do this immediately to avoid any data leakage in any application. And then here, okay, in blue is dummy IID data that I created by hand. In orange is the actual airline data set that I loaded from sktime. Second plot, I do IID bootstrapping on IID data that I created. The synthetic IID data is in black, and the other colored copies with the lower alphas are bootstrap copies. You see they're pretty much, statistically, they're pretty much the same. Scroll down a bit. Immediately it should be very clear why this doesn't work for time series data. All the temporal nature is lost if you do IID bootstrapping on a time series data set. This is where tsbootstrap comes to the rescue. I created it last August, and then Franz and another collaborator from sktime, Benedict, who isn't here, we worked for about 6 months or so improving the library and integrating it with sktime. And just as now, you just download an adapter from sktime, and voila, you have access to tsbootstrap. Also kind of reiterates a point I made earlier. sktime doesn't always, it makes a point not to reinvent the wheel. If it sees a project somewhere that's doing something that it doesn't have, it just creates an adapter, and you're done. When I created this, I had a few goals. Just like with sktime, the goal was to be in the sklearn ecosystem, use a very familiar API for folks. Same thing with tsbootstrap. It supports univariate and multivariate series. Currently doesn't support hierarchical data or hierarchical time series bootstrapping. But again, we are absolutely open to contributions, PRs, issues, etc. With time series bootstrapping, the most popular family of bootstrapping methods are called block bootstrapping. With IID bootstrapping, what you have, we looked at the image from earlier. You have, if you have 15 data points, each data point is considered singularly in its individuality, and then you just keep on replacing it again and again. You keep swapping things around. With block bootstrapping, when you apply it to time series, you kind of do the same thing, but you do it to a block. So if your time series is 1 through 15, you say my block length is 4. So now you pick a data of size, a chunk of size 4. So 1, 2, 3, 4, or then you can start overlapping 4, 5, 6, 7, etc. And then you start swapping those things around. The idea is to retain autocorrelation inside each block. And then depending on various parameters, the 4 most popular methods for block bootstrapping are moving, circular, stationary, and non-overlapping. Then tsbootstrap has access to, or provides access to, other commonly used bootstrapping methods. For example, these window-based methods, Bartlett, Blackman, etc. What it essentially does is within each window, let's say you have a window of 4, 1, 2, 3, 4. Each sample is weighted differently. So it's kind of it's a tapering window method to avoid edge effects when you combine blocks. So these are all made available from SciPy. So far, these have all been model-free methods, and then you can also have model-based methods. If you know that your time series has come from a particular or follows or respects whatever data generation process, we provide access to residual bootstrapping, distribution, Markov, and sieve. I wouldn't go into detail about this due to time constraints, but the idea is instead of bootstrapping the original time series data, what you do is you fit a model or n models hierarchically, sequentially, and you bootstrap the residuals. You add those bootstrap residuals to the original fitted data set, and now you have another bootstrapped time series data. You can also do this. There we go. This is, again, another mermaid diagram, which is showing the various type of bootstrapping methods and how they all mesh together. You can also, with these model-based bootstrapping methods that I mentioned, you can combine these with block bootstrapping. So when you're bootstrapping the residuals, you don't have to treat the residuals as IID. You can do block-based bootstrapping for the residuals. So for instance, you have Markov bootstrapping. There's a whole Markov class, and there is a block Markov class. Sieve bootstrapping. There's a whole sieve class and a block sieve class. Please go ahead and the README for tsbootstrap is quite detailed. The doc strings are very detailed, so take a look. For time constraints, I wouldn't be going into detail about the model-based bootstrapping methods. There is a table here. This is also available in the README for tsbootstrap on GitHub. It's copied verbatim. It shows you an overview of the different bootstrap classes and their salient features for when to use them, when not to use them. Same thing. Hopefully people have been able to load the data. There we go. Yep. This is data we loaded just above. Here, it's the same thing, but I just split it into a train and a test, and we clearly visualize it. We are going to be working with T1, the first time series out of a total of 48,000 time series available in the M4 monthly dataset. Okay. OS. OS is not defined. Interesting. I think this might be, I think, Franz, this might be like an older version. Yep. Oh, I have to define, because, yep. This is not good.
You need different environment,
Nope.
different notebook.
There we go. I think it's in this one. There we go. Now it's defined. Yeah, I don't know why it's causing so much issues, man.
Just clone it.
Did you, doesn't, I think you don't, yeah. I think this is an older version. It simply doesn't contain those files.
Oh, okay, so I should
think.
maybe pull break then,
Let's take a break.
5 minutes, and then we continue with usage of tsbootstrap.
It's 303. We'll start at 308 sharp. Just fix these little bugs. Debugging in prod is always fun. Do we want to use my computer?
Does it have?
No, it doesn't. Oh, you don't have. I don't have the adapter.
You don't have the adapter.
Never mind.
All right, so let's see. It's showing some diffs. So I'm just going to discard the diffs, okay? And pull.
Yeah, just go ahead and pull.
So there is a updated readme. That's not it.
Pardon me. Do you actually have the? Could you do ls? Do you have the figures directory?
Just going to pull the newest.
Thank you. Let's see. Dun, 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 dun. Yeah, why is there no such file at directory tsbootstrap? M4 monthly date. It's pickle. Yeah, can you run the file convertdata.py?
Oh,
Yeah.
where is it? Where is it?
It's yeah, it's right
So
there.
I should run this one. In which directory?
It's in the root directory.
Okay, so run it here. What is it taking? How long is that supposed to take?
On my computer, it took like 45 seconds.
All right.
So
Let's
I'm
see
not
which one
sure.
is faster.
Shouldn't take more than a minute. What is this, like a 16-inch or 17-inch? It's a huge laptop.
Yeah, yours is faster.
It's also newer, so that's whatever. Yeah, it'll run. We have time.
Yeah, yours is much faster. It feels like I'm having the slowest computer here of everyone. I've been running from air conditioner to air conditioner today.
I don't know why they blast the AC in here. That's insane.
Oh, it's nice and cool.
Yeah, I was totally glad you didn't. 45 seconds.
It's now already at 3 minutes. Can we do without it? Do you have the cells executed already? Well, you have the cells executed already, so why don't we just...
Do I?
Well, I'm not sure what should be here in the display, but everything below that looks like it is.
Could you go up? Yeah, why isn't it displaying here though? That's the thing.
I don't know.
Yeah, the figures are available. I can just show the figures by hand, that's okay. All right, let's just start. No, I need it all, open the window, I need it to read it.
Okay, give me a second. That window?
Yeah, side by side, this window and that window.
Like this?
Yep.
Okay, so do you want to show
That's,
all of
that's
them?
okay, it's okay, just
So you
say-
can do this
Yep.
here, okay?
Okay.
Yeah. So
I got it.
Should I close this?
Yep.
All right. Here's the window.
All right.
Should we move this to the right half?
That's okay, no, that's fine.
Okay.
All right. Okay. I'm just gonna wait one more minute. I think that gentleman is coming, and there we go. Okay. I showed a plot earlier with what ID bootstrapping looks like. Now, before going to code, I want to visualize what moving block bootstrapping looked like. We talked about 4 different types of very popular block bootstrapping methods, which tsbootstrap provides access to. Here we see what moving block bootstrap looks like. Your original time series data was 1 through 15, and then we have 3 draws. We've picked here, for demonstration purposes, a block size of 3. That's something, if you don't provide to tsbootstrap, there is some like old literature out there that says one good block size is the square root of the length of the time series, and that's the default. But here by hand I've put block length as 3. So you see there is an overlap. If you notice, 13, 14, 15, but 12, 13, and 14. So there is an overlap of 1 unit. That is a parameter that goes into it, and by default, overlap is 1. You can have blocks overlapping, non-overlapping, but in literature, when we talk about moving block bootstrapping, it comes with overlap. So you have a block length of 3, an overlap of 1, and you can't wrap around. If you notice, there is no 1, 2, 3, or 2, 3, 4, because that simply didn't get picked up in the first iteration, in the first draw. In draw 2, you have 14, 15, and 1. It's CBB. This is circular block bootstrapping. It's the same as what I defined, but it just enables to loop around. In the second draw, it gets picked up because resampling or bootstrapping is resampling with replacement. It's possible that in some draws, some samples simply don't get picked up. And the same thing for draw 3. We already looked at IIT. This is MBB, moving block bootstrapping that I talked about. Exact same thing as what we saw, but it doesn't allow loop arounds. So you cannot have 14, 15, 1 or 15, 1, 2. The last block you can have is 13, 14, 15, which is kind of what you see, 13, 14, 15. This is a non-overlapping block bootstrap. You just take away the overlaps. If one block is 1, 2, 3, the other block has to be 4, 5, 6. And this is stationary block bootstrapping. I won't, again, go into the reasons why, but let me zoom in a little bit. Okay. Before I mentioned I picked a block length of 3. You don't have to pick a uniform block length. You can stipulate that the block length is drawn from a distribution, and you can give the parameters of that distribution. Specifically, stationary block bootstrap draws the block length from geometric distribution. So I give the parameter 3. Now 3 becomes a parameter for my geometric distribution. But if you notice in these plots, for example, in the very first cell of draw 2, the elements picked, the block is only 9 and 10 because that block length is no longer fixed. You can have block length, again, 6, 7, block length is 2 because it's drawn from a geometric distribution. And tsbootstrap provides access to literally every distribution that SciPy provides access to because it just imports from SciPy. Yeah, and that's it. So this was just to motivate before we start looking into the code, what these most popular family of bootstrapping, time series bootstrapping methods, they actually do to your time series. So that was kind of essentially what I had in the cell, which isn't rendered here, was those 4 images in a 2x2 grid, but it didn't render. That's okay, no. Why isn't this should at least work, right? Okay, this is not work, we just installed the whole thing. I don't know that we have an option, but move on. All right, we're gonna move on, no worries. In the plots that I showed, we covered a few important aspects. We covered something called block length. We covered block generation, and then there is block resampling. So these are really the 3 essential ingredients. We're going to go through these. These are the 3 essential ingredients of block-based bootstrapping. There is a class in tsbootstrap called block length sampler, which feeds into block generator, which feeds into block resampler. And we start with block length sampling. Why it's important, it's just a first step in block-based bootstrapping. In tsbootstrap, there are various strategies for block length sampling. Impact, it affects how much of the original data structure is retained. And it provides you, these are the various parameters. Average block length, like I mentioned or demonstrated through that example, we picked 3 as the parameter of a geometric distribution for stationary bootstrapping. There are multiple distributions provided, not necessarily with just 1 parameter. Sometimes you can have 2, sometimes you can have 3. You can say, I want my block length to be picked from a standard distribution with this mu and this sigma. You can do that. Sensibly, it also has text on it. What if your original time series data is of a length 100 and the block length picked as 200? That doesn't make any sense. So it'll cut it off. All those are tested with hypothesis in the back end. So it's quite robust. Block length distribution. And then the key method is sample block length. You can, if you want to modify, play around with this class, you can do that, but this is all done internally. So how does block length sampling work? Simply, you import, and you literally call .sample block length. By default, since we did not provide a block length, it's set to 2, and all of the sample block lengths are 2. Let's say I want to I want to use the normal distribution. I do not provide any parameters. There are default parameters. It'll use those since I didn't provide any. The standard 0 and 1 for mu and sigma. and it'll start, if I run it 5 times, it'll give me 5 different values. Sure. What happens if we, hold on one second, block length sampler normal, dun, 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 dun. Oh yeah. Here essentially what I'm trying to, again, I don't know, this is like an older version. The point I was trying to make here was a block length sampler also takes in an RNG parameter, so you can set a seed. Let's say you wanted to sample from a distribution. You did this 5 times, you get certain number of block lengths. You try it again, and you get completely different points. And now if you wanted to test something, it's not replicable. So we provide a capability where you can provide a generator, a seed, whatever you want, so things are replicable. Okay, just so funsies, you can have Poisson distribution with average block length of 4. You sample it 5 times, and you get 5 different block lengths. These block lengths feed into the block generator. Now you know how large your blocks will be, and now you start generating those blocks. I mentioned in the figures that I showed, sometimes those blocks can overlap. Sometimes they can sort of flip, they can completely converge around, wrap around as the parameter here. You can have a minimum block length. You can, when you draw these things from a distribution, you can say the smallest block I will allow is of this size. And the main method here is generate blocks. We do the same thing. We start playing around just to demonstrate how these things work. You import block generator, and you feed it the sampler the block length sampler that we created above, and you say the original time series is of length 10. Then it creates for you these possible blocks with the configuration you gave it. So I said overlap is true, and by default it takes the block length to be 2 and the overlap to be 1, and doesn't allow a wraparound, which means you're really left with no choice. These are the building blocks. These are the Legos that it's creating. It's saying 1 block is 0 and 1, 1 and 2, 2 and 3, 3 and 4. The fact that there is no wraparound, which means it's kind of going from the end first. And in the very last step, where we resample these blocks, that's where we will impose the constraint that the final time series generated by the stitched Lego blocks has to be equal in length to the original time series. That constraint isn't imposed currently. We're literally generating the Lego blocks. What if I say there should be no overlap, which means the only possible blocks are 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9. These are the only possible Lego blocks. Finally, block resampler. You create a block length sampler that feeds into the block generator that feeds into the block resampler. Same thing, please feel free to look. I feed it the blocks that were created, and then we resample it. There we go. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. It stitches these blocks together, essentially. Now that we have these different blocks, we can literally treat it like IID bootstrapping, resample with replacement. That's what this thing does. I mentioned earlier, with block bootstrapping, the idea is to create blocks and then start doing IID bootstrapping on the blocks. You can't do IID bootstrapping on the original time series data, or you'll lose a lot of information. With that background, I know that was a lot, some hands-on stuff. What does this actually look like with the data set that we have at hand, which I'll remind you is the M4 data set. So another thing that when you call .bootstrap, just like with a cross-validator in scikit-learn, the output when you do .bootstrap isn't a list, but it's a generator. And I did this by design, so you can play with very large time series data sets without the memory issue popping up. Here, I have our 4 block bootstrapping methods. Bless you, Franz. We go ahead, we had done the train test split. We go ahead and recreate here. Here, essentially, we are saying that let's check everything is okay. I wanted 100 bootstrap copies. The original training data was of size 381, which means the final data set that was created was a size 100, 381, which means now I have 100 bootstrap copies. This is just to verify that everything is going well. Since it's a generator, the generator is exhausted once you go through it. So you, again, for demonstration purposes, I bootstrap again. And now I start actually forecasting. Okay, so this is a utility function. Here I use theta forecaster with a given look-back window, seasonality of 120 days. Essentially, what this function will do is it'll forecast using the original time series data and a forecaster, and then it'll also make bootstrapped copies, and it'll forecast using the bootstrap copies. Original time series data feeds into a forecaster, you get forecasts. Bootstrap copies feed into the forecaster, you get different forecasts. Again, these are utility functions here. This is to print the summary. Plotting, the really important thing is here. There we go. This is sort of the money plot, if you will, with moving block bootstrapping with a very simple forecaster, theta forecaster, that there has been no sort of HPO or anything done like that. We pick moving block bootstrapping, and we try to get the confidence intervals. Performance is meh. To be honest, the original forecaster didn't fit very well, as you can see. But the goal here is to demonstrate that literally by creating bootstrap forecasts and calculating the confidence interval, you can now just be more certain in your estimates. And now this can either be the end, or it can form part of a pipeline where you feed this into something else. Here is circular block bootstrapping. You use circular, gives you a better coverage, I would imagine, or we can actually see coverage is significantly better. Here we don't cover the top parts, and here with circular block bootstrapping we do. It kind of makes sense because circular block bootstrapping wraps things around, and there is a seasonality, a circularity present in our sales data. Same thing with stationary block bootstrapping, where block lengths weren't fixed but drawn from a geometric distribution. And we do the same thing with non-overlapping block bootstrap. I'd mentioned a variation of the blocks, the weighing of the blocks. For that purpose, we used tapering windows functions. These are all drawn from SciPy. So first, let's visualize what these functions look like. If you go actually read the README for tsbootstrap, it says when to use these different tapering functions, and depending on your data set, you can feel free to explore. You can do trial and error, whatever works for you. The idea is for each block, we want to assign lower and lower weights to the endpoints and higher weights to the middle points, so that when you sort of mesh those blocks together, there isn't a drastic shift. You're absolutely welcome to compare the description here to the image we have up there. We provide 5 types of windows, and it's extremely trivial to code up your own custom window and feed that in. I mentioned how these could be relevant to the M4, or in general, what kinds of data sets to use these with. Just a pro tip before I actually apply these bootstrapping methods, it's always a good idea to play with different window types and lengths and see on your train and test data sets what kind of performance you get before pushing anything to prod. Same thing that we've done before, we're fitting these 5 window functions, bootstrapping methods to our selected time series data. By default, these bootstrap classes, they inherit from moving block bootstrapping. However, you can have them inherit from circular block bootstrapping, from non-overlapping block bootstrapping. You can compose your own classes. All this really does is it applies a tapering function. The back end is moving block bootstrapping. Enough talk. What does the output look like? Here we verify that everything is fine. That's great. Okay, this is with the base parent moving block bootstrapping, where all samples in a block are weighted individually. We've already seen this before. Here it's shown again for just to refresh your memory. Here we start with the Bartlett window, and you can see if you just scroll up and down a little bit, the coverage has already improved, especially in the top area. For instance, right here, we actually don't go past the ground truth value, which is not what an upper confidence interval should do, and suddenly here we do. So these windows actually play a very important function. Blackman bootstrap, different window function, same thing. I won't be redundant. Handing bootstrap, you can create your own, and these are just the 5 that are available. Okay. So this sort of concludes this particular notebook. To recap, we've gone over what bootstrapping is, what regular IID bootstrapping is, the different applications of IID bootstrapping, why it doesn't suffice for time series data, and then we got introduced to tsbootstrap and block-based bootstrapping methods, and what are the components that go into creating a block-based bootstrapped data set. We talked about block length selection, we talked about block generation, and once we have that, then we talked about block resampling. You combine these together, you have the parameters you can play with are how much to overlap one block with the other, how much to weigh the numbers inside the values inside each block, whether to allow wrap around or not, etc. And then we demonstrated visually on one particular data set, time series data set from the M4 monthly larger data set, what this performance looks like with a very simple theta forecaster. In the next 2 notebooks, Franz will go over how this tsbootstrap, how it meshes very finely with sktime, and he'll talk about some other functionalities that are important for uncertainty quantification at large. Okay, thank you.
Thank you. Yeah, I think that was quite a trial by fire, fighting against the machine valiantly. Yes. Well, so is that debut at a big conference, or was it the first trial by fire at the software? So. All right, so maybe I should quickly also mention, this is something, so if you see this function here, you can also, there's an adapter in sktime, it's called the tsbootstrap adapter, and you use it in the bagging ensemble, then it's a few liner. I will show it in the next notebook. Now, for the next 2 notebooks, we're going to take one step back, but then we'll also get back again to the bootstrap. So what we will have a look in this notebook number 4 is probabilistic forecasting again, but then we dive more deeply into the different types of probabilistic forecasts we have in the sktime interface from different possible methods, then looking at the metrics for different types of probabilistic forecasts, evaluation including backtesting, and advanced model composition patterns for probabilistic forecasts. And as standard guide, we've said sktime is easy to extend, new methods are easy to add. Also briefly speak about that in this notebook. All right, so this vignette we've already seen in the previous notebook, just to remind you of it. Very similar to scikit-learn, data specification. Then we specify the algorithm, so it could be a theta forecaster, but we will be looking also at composites like bootstrapped versions of non-probabilistic algorithms in this notebook. Everything has the same interface as if it's a forecaster. So dot fit, Y forecasting horizon, Y can be multivariate, it can be hierarchical, and predictions are then obtained by ypred. So probabilistic forecasting, again, reminding you of what we saw in notebook 2. We have specific methods for different types of probabilistic forecasts. So instead of this point prediction method, predict, we would call in sktime one of the probabilistic methods, for instance, predict interval. This asks for a probabilistic interval forecast at nominal coverage 0.9. We've seen that as well in notebook 2. So we expect in 90% of futures, of plausible futures, the actual value to be between the lower and upper bound produced by the forecasting algorithm. So plotting upper and lower here. So blue is the past, orange is the future. Again, repeating. There's 4 different methods. Every probabilistic forecaster has all of them. So either a forecaster is not probabilistic and it doesn't have these, or if it has them, it has all of them. And say if it has a quantile prediction or a variance prediction only, and if nothing specific is assumed about the distributional form, it's assumed to be a normal distribution, a normal predictive distribution. We've also seen in notebook 2, can use the all estimators registry utility to filter for the capability predict int, which covers actually all of these 4 methods. So you have to filter for the value true. You can also use, we have very recently an estimator search online, where I can do the same thing directly in the API reference on the web page. Okay, now let's look in more detail at these 4 interfaces, at what they exactly do, and what the inputs are, what the outputs are, how it behaves in the presence of exogenous data. So theta forecaster is one of the forecasters that does implement probabilistic forecasts. Predict interval produces interval predictions. So prediction intervals, just to repeat, so interval is a prediction interval is a prediction for a given time point in the future of an upper and a lower. The coverage, the nominal coverage of the prediction interval says the algorithm believes that coverage fraction, so 0.9 means 90% of plausible futures take place in that interval of lower and upper, and you have the same for every timestamp that you make a forecast for. The time index is determined by the forecasting horizon, which can be relative or absolute. And the output is a pandas data frame of this form. You can pass multiple coverages, so that will be here the second level of the column multi-index. The first level is the variable, so if you have a multivariate, you make a multivariate forecast, you have multiple variables here, you have multiple coverages, and then you have lower and upper. So we see here, for instance, for January 1961, this algorithm thinks that the value in 90% of plausible futures will be between 418, 464. As a plot, again here. So this is prediction intervals, right, between lower and upper in coverage percent of plausible futures. If we have multiple coverages, then this second index, second column index, you have more of these, so you can say I want a 50% coverage, 90%, 95%, and in 95%, of course, you're very sure that it lies in this interval, but of course, again, not absolutely sure. And very importantly, I want to stress, that's what the algorithm thinks, and algorithms can be wrong. So if you have 95%, that's what the algorithm says, and there's some caveats I'll come back to at the end. For instance, detrending, deseasonalization. So a probabilistic forecast can be wrong. Should keep in mind, so even though there's a statement in 95% of plausible futures this will happen, this is a statement of the algorithm that might be wrong. So we'll get back to that in how we evaluate these statements for algorithms. Predict quantiles. What is a quantile prediction? Predict quantiles makes quantile forecasts or quantile predictions more generally. So here we pass so percent points, or here alphas in the interface. What does it mean if we ask for alpha equals 0.1? So that says in 10% of plausible futures, the value will be smaller. So the algorithm thinks the total number of airline passengers in January 61 will be 423 or smaller in 10% of plausible futures. It will be 423 or larger in 90% of futures or realizations. And you can ask this, of course, for multiple of these points. So, of course, if you take 0.25, you would expect the value to be larger because there are more futures, so 25% off, as compared to 10% of futures that you would expect, in which you would expect the value to be smaller.
It's like similar to percentiles.
Yeah, these are predictive percentiles. Yeah, so I mean, there's a bit of a terminology precision. So these are actually percentiles. So predictions of percentiles at these points. The values that are being predicted are the quantiles of the predictive distribution. So we'll look at how the predictive distribution relates to all these. We'll look at this in another go across everything. Other questions? So it's maybe, if you see this for the first time, it's not straightforward to get your head around, perhaps, yes? So the question is, are we explicitly predicting the quantiles rather than calculating them from simulations, so trajectories under the hood? So the answer to this is up to the algorithm. What I'm demonstrating here is only the unified interface. So there are algorithms which do what you say, they directly predict quantiles. And those are, for instance, algorithms minimizing a quantile loss directly. So these algorithms, they do not make distributional predictions, or they do not carry out Monte Carlo simulations. Of course, other algorithms, and that's up to the algorithm what it does internally. So think about it like a power cord connector. What you plug in can do what it wants, or think about it as a piece of equipment in a car. So internally it might choose to do simulations. Internally it might just go directly for minimizing a loss. So sometimes the one thing can be advantageous, sometimes the other. Typically, if you know what you want as an output, directly minimizing that objective tends to be more effective, more accurate. But again, that's more of a rule of thumb than a general statement. So this is the general interface, whether the algorithm now internally does trajectories or Monte Carlo simulations, or whether it is a quantile fitter. This is the output that you get from predict quantiles. So what sktime and sktime compatible interfaces also take care of is mapping what the algorithms do on these interfaces. So for instance, the primary output might actually be predict distribution, because you get an empirical sample from a Monte Carlo simulated posterior, for instance, and then it derives predict quantiles from that. Or the primary output could be it could be the quantiles or even just the variance. Then you still have access to the other method, because, for instance, sktime posits a normality assumption, and then it derives the normal distribution and then all its quantiles from the prediction of mean and variance. So here is different quantiles. So you can imagine these being high, low, mid scenarios, again, according to the algorithm, and the algorithm may be wrong. So you see, for instance, here, and that's again a typical thing, if you apply it naively, it doesn't model things like trend very well for most of the algorithms. So you have to think about the trend. You already see it here, so you get high and low scenarios, but it's missing the trend in this very simple prediction, and that has a reason that I'll explain later. Predict variance. So predictive variance, also a volatility prediction if you're more of a finance persuasion. Predict var predicts the predictive variance around the predictive mean. And that's a single number, so it's of the predictive distribution, the variance for the predictive distribution implicitly assumed. Predict proba predicts a full distribution object. I will not go into distribution objects here in detail. I will do that in the 5th notebook. But there is a specific unified interface for this distribution object as well. They behave like pandas objects with subsetting. You can see it has here, it's a normal distribution with mean. The mean here is 2D array-like, and it has the variance, but it could be a different type of distribution, and then it wouldn't be parameterized by mean and variance. It could be entirely non-parametric, so it could be an empirical distribution if you obtain it, for instance, from a Monte Carlo simulation. But it's mapped on the same interface point here. The distribution itself has different methods. So what you can do now from this distribution to obtain predictive quantiles. So from the distribution, once you have it, you can actually obtain all the other quantities. There's a small note here on consistency. The framework, so sktime, does not enforce consistency between the outputs of the different methods. That is left to the implementer. It is not directly tested. For the algorithms in sktime, these should be consistent, but there are some cases, for instance, where a method only produces predict quantiles, then predict proba makes a normal assumption on interquartile range, and then it's not actually consistent. So you should also be careful on about consistency, because the framework interface does not enforce it. The docstring, the documentation of the particular algorithm may give further information on whether these 4 methods are consistent with each other. So predict interval, predict quantiles. If in, I would say 99% of cases, these are consistent with each other, because it's easy going from one to the other if you assume symmetric coverage of prediction intervals. Predict proba is, I think, the one where you have the largest amount of inconsistencies between. So it's not strictly enforced. Of course, for the first party, so algorithms directly implemented in sktime, we try to be consistent, of course. Any questions about these 4 interface points before we proceed? All right. So how does it look like for multivariate and hierarchical data? We've seen in notebook 2 that if you apply a univariate algorithm to multivariate data, it automatically broadcasts. So it applies itself to all the variables such as a GDP or population. If your data set is hierarchical, you have things like product groups, and within these product groups you have your own sales over time per product group or per product. If the algorithm is not hierarchical, it broadcasts itself across. This is true equally for the probabilistic methods. So if we use, for instance, a vector autoregression on a hierarchical data set, or ARIMA on a hierarchical data set, so this is it almost looks like the M4 dataset, but I'm not using the M4 dataset here. And if you apply to this dataset, and predict interval will also broadcast in the same way. There's also a nice feature that is not shown in this notebook, but which I want to mention for broadcasting. So especially if you do probabilistic predictions, it's useful. This is, of course, if you have a univariate or a non-hierarchical algorithm, it is embarrassingly parallelizable. So you can select a parallelization backend other than just a simple loop, for instance, joblib and any joblib compatible backends or Dask via setconfig on the constructed estimator. So you can do forecaster.setconfig, and the setconfig documentation has options for the backend. So this is actually parallelizable if you have a larger amount of hierarchy levels or a larger amount of variables and hierarchy levels combined. Okay, so we've seen probabilistic forecast methods. They mesh well with hierarchical and multivariate forecasting. Simply get broadcasting as well of these methods. For predict proba, it's not fully implemented yet, but that's also on the roadmap. So how do we know whether probabilistic forecasts are accurate? We've seen above, you ask any algorithm that is capable of probabilistic forecasting, and you get a thing like this. So is this actually good or not? Is it a problem that the trend is not captured? How do we know that the algorithm is actually good at making probabilistic forecasts? Because even if the algorithm says I'm 95% sure, it might be 95% sure of something wrong. The stylized answer to that: evaluate in an unbiased, in an uncontaminated setup, and for that you have the combination of metrics for probabilistic forecasts and evaluation. So I will not go into detail about the metrics now. What I want to show is how this evaluation workflow works in principle. The workflow, if you're familiar with scikit-learn, is the same, except that the metrics are specific to probabilistic forecasts. So you get actuals and predictions, you specify the metric that you want to use, and you plug the actuals and predictions into the metric. That gives you a single evaluation. You may want to do this, and in generally want to do this inside an evaluation setup with temporally aware cross-validation, so backtesting schemas, for example, using the metric. Well, let's look first at the metric, and then let's look at the evaluation. So one example, quantile forecasts. So if you want to evaluate a quantile forecast, then you need to compare quantile forecasts against actuals, which aren't quantile forecasts, but they are actuals from the time series. So you have, for instance, the y-test here. That's so we cut the time series in two. So of course in backtesting you do this multiple times, but for a metric we do it once. We make the forecast once at multiple quantiles. Here that's our forecast, quantile forecast at multiple quantile points. The quantile metric, or the most common quantile metric that you would use, is the pinball loss. also known as the hinge loss or simply the quantile loss. This one aggregates over all the quantile points that you have predicted, and also takes the mean across all time points if you don't specify it otherwise. It's a class. If you once you instantiate the class, you can compare the true values. This is simply a univariate time series with the predictive quantiles. The predictive quantiles are this data frame here with the multiple quantile predictions. This gives you a number. You can also do this by time point if you want. For that you have to use the evaluate by index method. Not shown here. Quickly want to mention it. If you have hierarchical data, then there's the multi-level argument of the metric. If you have multivariate data, then there's the multi-output argument of the metric, which you can use to control the aggregation across variables and across different levels of hierarchy. So if you want to know what was my loss in a different product group, you can do that as well with the class. Consult the documentation for that if that's something that interests you. More about different types of metrics later, because now I want to show backtesting. So just doing a single split and then evaluating has the key problem here is that that you are aggregating different horizons. So you may not want to aggregate different horizons. You may actually want to sample multiple instances of where you predicted, say, 1, 2, 3 step ahead and aggregate over those. So you want to get a higher effective sample size of forecasts at the same horizon, whereas these here are different horizons. For time series forecasting, doing simply this and maybe computing the mean would actually be problematic. And that's why you typically do backtesting. And in backtesting, you specify a temporal aware resampling scheme. Here, for example, we have taken the expanding window splitter. The expanding window splitter cuts multiple times, so across your time series, cuts off different growing parts, expanding parts, makes forecasts at these different cutoffs. So here in the table, for instance, we cut off every year, end of every year. We make a forecast for the 3 months. So what we're doing here is we have 5 different splits in which we predict the next quarter from the end of each year between 54 and 58. The results table allows you to look at the results. So these are aggregated now over forecasting horizons. For each of the years, you can also aggregate across, of course, by computing the mean here. In case you're wondering, you can also weight. So as in weighting, so not as in I'm waiting for, but I'm weighting, I'm assigning different weights to the different forecasting horizons. You can do that as well as one of the arguments to the losses. So each row here is one train test split, and the first column is the evaluate of the loss. And if you look at the parameters of evaluate, again, you can do things like parallelization. You can ask to return further columns. Yes?
This is essentially cross-validation or not, because your test was
So the question is this essentially cross-validation? So yes and no, depending on your definition of cross-validation. The narrow definition of cross-validation shuffles the data, the timestamps uniformly, which would be a bad thing in the temporal case because you have autocorrelation. So if you do that, you're actually not forecasting, you're predicting timestamps all over the place. You're using temporally aware splitters. Now, what the sktime splitters additionally do, they also handle hierarchical data. So you can do this evaluation also in hierarchical data. It handles multivariate data. sklearn splitters also do that, but it's basically wrapping around this time series structure that sktime provides. So it's cross-validation in the sense that it does split your data. I think a more accurate term would be splitter. It's a term also that scikit-learn use, so time series splitting. And it's not cross-validation in the narrow sense where you shuffle.
So that makes sense. So for each split, I realize your window, your test window is shifting, right?
Yeah.
As your test window shifts out, are you training on a larger set each time?
Yes.
This is an expanding window splitter. You also have a moving window splitter, where the window size is that.
So you could also select here, by the way, whether you refit or update each time you expand. You can select a strategy which is not expanding but sliding. You could even select a strategy where you bootstrap the chunk. Now that would be nice, integration of this chunk bootstrapping, or I think there's the expunged bootstrapping and whatnot, these advanced resampling methods. They would in principle all fit into the splitter interface. So splitters are first class objects in sktime, so you can also list them, all estimators, and then the type is splitter. There's about a dozen there, which all relate to different things we can do with time series. So, yeah, in principle, the most popular ones I think are expanding window, or where you start cutting from the end. That's useful if your time series are not all the same length. That's called the what's it called? Greedy something. You can look it up. So let's do this live. And we do all estimators. It's split or splitter? So expanding greedy splitter. Yes, the most commonly used ones are probably expanding greedy splitter, expanding window splitter, and sliding window splitter. And there's some other splitters which are focused on making a single split or making splits depending on dates you prescribe. Whereas the parameterization of the expanding greedy splitter and the expanding window splitter is in terms of window length. So relative, whereas the cutoff splitter has absolute cutoffs. Any other questions related to splitters or evaluation? So you can also find a larger notebook about benchmarking in the sktime repository. There's also, I think, a workshop we had at, I think it was PyCon Prague last year, where benchmarking was a focus. The one difference here is, or the gist of this is, you can do all that, but you just put in a probabilistic metric and it still works. Okay, so this section is also of a similar direction. So you have different composition principles, feature extraction, pipelines, tuning, AutoML. There's also dedicated notebooks about that, but I'm showing this here with probabilistic forecasting. There is not much specific about probabilistic forecasting except what happens in pipelining if you change the, if you apply a transformer to the output, and reduction, which are specific to probabilistic forecasting, as in you have a forecaster that is a point forecaster. How do we turn it into a probabilistic forecaster? One option, of course, is using tsbootstrap and a tsbootstrap adapter to wrap it around a point forecaster and turn it into a probabilistic forecaster. Okay, and that's what we start with. Reduction to, so reduction as in reduce one problem to the other. We reduce the problem of making probabilistic forecasts to the problem of making point forecasts by applying an algorithm that creates an algorithm for the one from an algorithm that does the other. So, exponential smoothing. Of course, there's variants of exponential smoothing which are probabilistic, but the exponential smoothing, this estimator here in sktime is not probabilistic. So how do we add prediction intervals, or how do we make predictive distributions via some principle, some algorithmic principle? So there are two stories here. There's the algorithm perspective. So what is it that we actually do in logic? And there's the interface perspective. How does it look like in specification in terms of Python classes? So in terms of specification, this looks like a class that you construct with the forecaster where you want to add the probabilistic prediction mode. And the result is again a forecaster, but it now has the tag turned on, capability prediction interval. And so this is a naive variance. What it does is just do sliding window, compute the residuals, and the residual variance is the variance we predict for a normal, for a given forecasting horizon. So it's pretty simple algorithmically. Interface-wise, this is how it looks like for any composition that adds probabilistic capability to a forecaster. So you take any forecaster, see here my forecaster, exponential smoothing, and then we wrap it, so we apply an algorithm to it, which is constructing the class, so constructing an instance of the probabilistic wrapper with the forecaster. And the composite is a forecaster, so interface uniformity. This becomes part of the specification, so step 3 or step 2, depending on the vignette, and now it has all the methods. So wrappers of this type currently in sktime, so indexed by sktime, of course you can write your own if you want, and you don't need to share it with the world, or you can write your own in a separate package, and then it lives in a separate package. And it's still indexed by the search function. So we have naive variance, squaring residuals, conformal intervals, ENBPI, which is also a variation on the theme of conformal intervals. This one uses code from Amazon Fortuna. Bagging forecaster takes two components. So bagging forecaster takes a bootstrap algorithm, which is a series to panel transformer. So it takes a series and creates multiple series to it. We saw that in notebook number 3. A bootstrap algorithm in its interface abstraction takes a series and creates more. So for instance, scenarios of the same past or scenarios of future forecasts. So it is a transformation, it's a specific type of object, and the bagging forecaster takes both as an argument. So it would look like, maybe I should write it down because we have not seen it in the previous code. So we have, let me see, from sktime forecasting, I think it's an ensemble, is it? Oh, it's in compose, import bagging forecaster. I'm just going to show you the docstring of it. So it takes a bootstrap transformer, which is by default the STL bootstrap transformer. But what it could be, so you could alternatively pass to it the tsbootstrap adapter, which takes a tsbootstrap transformer, and a forecaster. Okay, so it also takes a seasonality, seasonal period, but it's only used if you pass the STL bootstrap transformer. So these two are the key arguments. for the bagging forecaster. And if you combine the bagging forecaster with the bootstrap transformer, it's basically creating bootstrapped forecasts. Okay? Any questions specifically? So interface-wise, it's the same. It produces, you construct the estimator with the bootstrap, with the forecaster, and it adds to the forecaster. If it didn't already have that capability, then it adds it. If it had it, then it overrides it. Probabilistic forecasts capability. And the capability, as in if you call predict interval, it will create those prediction intervals by using the bootstrap algorithm. Yes? All right. Okay, so moving on to tuning and AutoML. Specifically for probabilistic forecasters, this should all mesh as well with probabilistic forecasters. So we have, of course, grid search, random search. We have also dedicated wrappers using Optuna and scikit-optimize for tuning the parameters of a forecaster. So the way it works, now I'm showing it for a forecaster that is already probabilistic. If it's not probabilistic, you have a choice which one to apply first. So let's say I want to tune the seasonality in theta forecaster in a non-parametric way. Then I can pass the probabilistic loss I want to tune for to any of these parameter tuning wrappers. And here it will tune the seasonality parameter over, so no seasonality is 1, 6, or 12. Interesting bit, interface uniformity, it's again a forecaster. Yeah, so it has the familiar fit, has a familiar predict interval and predict interface, and it has the components, the evaluation schema, so that's here the sliding or expanding window splitter, the forecaster, and also the loss. All of these are first order citizens in sktime, so you could choose another cross-validation schema, you could choose another forecaster, and another loss function. Inspecting best parameters in best params, that's the interface we've chosen there is exactly the same as scikit-learn's grid search. As I've already said, obtaining predictions, unified interface, same method, using predict interval. Any questions about the grid search? So something I'm not showing today is you can actually also tune things like seasonality using a seasonality estimator. So for instance, using autocorrelation functions. For that you can use a parameter estimator module. So you don't need to do an exhaustive or an evaluation-based tuning. You can actually also do statistical estimator-based tuning. So I can have a look at that in the forecasting tutorial if you're interested in that option. Any questions about grid search? Okay. So AutoML, so often it's stated, okay, AutoML is very different from grid search or from tuning because you actually also choose the forecaster and not just the parameters. But it's the one is a subcase of the other if you make the forecaster a parameter. So if you expose the choice of forecaster as a parameter, and that's what the multiplex forecaster does. And if you combine that with forecasting grid search, you can also do AutoML for probabilistic forecaster here. Just a very short mention. Because AutoML always comes up where you show tuning, but you didn't show AutoML. So one is a subcase of the other if you use the multiplexer. Okay, finally, and here's again where things become special or especially influenced by the fact that it's probabilistic. Right? So tuning, same as if it wouldn't be probabilistic, but you pass a probabilistic metric. You have two choices. So first you tune, sorry, I'm starting over. So if you do tuning of a probabilistic forecaster that you turned into a probabilistic forecaster by applying a probabilistic wrapper. You could do tuning first and then do the probabilistic wrapping, or you could do probabilistic wrapping and then tune. So in the first case, where you first tune, you can't use a probabilistic metric. Okay, so you're not actually tuning the metric you want because you don't have access to it, because when you tune it's not yet probabilistic. In the second case, so you do the probabilistic wrapper and then you tune, you do have access to the probabilistic metric, but you might get a double loop over, also each time you do the sliding window in something like naive variance or conformal intervals, you do the tuning loop inside, which might give you a lot of computational overhead if you try to do it that way. So one trick is to choose a less computational update mode in the tuner. So if you have update params or update behavior available in the tuner, you can try to tune it only at the start or not as often. Any questions about tuning before we move on? Okay, so pipelines. And these pipelines are also general. They apply to non-probabilistic forecasters as well, but there are specific things that happen in the probabilistic case. So the forecasting pipeline is a pipeline for exogenous data, for transformations with exogenous data. So if you think about feature extraction, differencing, deseasonalization, you have a chain of transformers, and the forecasting pipeline, which is the pipeline for exogenous data, applies the transformations in this sequence. So it first applies the first transformer in fit. So it does fit transform, so it fits the second transformer and the output of the one, and so on. In predict, it then transforms in sequence. Okay, so this is the exogenous data. On the exogenous data, we're not doing anything probabilistic here. So let's say we use, so ARIMA is actually SARIMAX. It can use exogenous data. We may want to impute exogenous data, then we chain an imputer with a forecaster. The result has predict intervals. So if the forecaster is probabilistic, then this pipeline is also probabilistic. And what it does here in the last step, it simply applies the probabilistic method of the forecaster. Okay, so it applies the transformers in sequence, and then on the result in predict, it applies the same method in predict. So nothing specific or nothing funny happens in the probabilistic case. Okay, because this is exogenous data. Now, if we look at the endogenous data, then the logic is a bit different because we need to, so if you think about differencing, so we had making the series stationary, for instance, but we need to invert the differencing after predicting, because that was the endogenous data. So on fit, we do the same thing. Fit transform, we apply the chain of transformations, but then in prediction, we need to apply the inverse transform. So endogenous data. So if you first difference, then you forecast, then you need to invert the differencing so it's in the same on the same scale, the same space. And what it does for the probabilistic predictions, it applies the inverse transform to the predictive quantiles. So what it implicitly assumes is that the transformation is monotonic. If the transformation is not monotonic, then this is actually incorrect. Most of the transformations for, say, pre-processing, scaling, the monotonic transformations. If you have a non-monotonic transformation, then of course you need to be careful here. Okay, then the remaining ones, they're inferred from predict quantiles. Questions? So if it gets too esoteric, please let me know. We're talking specifically about probabilistic predictions. So of course how it looks like in practice, I chain a disease analyzer and a detrender. So then you apply a REMA, make a probabilistic forecast, and you reapply the trend, which in that case adds an offset to each forecast, and adding that offset is an invertible transformation, so things are fine. Today is not the pipelines tutorial. Just want to mention again, so this transform target forecaster you can also create with the Dunder method, so times multiplication means you chain endogenous. If you do this, so with the double multiplication you chain to exogenous. So it might be quicker for templating. Of course you may want to be careful because it's more prone to typos. Okay, so these are the major building blocks from the perspective of probabilistic forecasting. Feature extraction transformations go in here as well in the pipeline. So if you have been, say, to the Temporian workshop earlier today, we have an adapter for Temporian. It's quite efficient and effective for feature extraction, for transformations. So you may also want to apply the Temporian transformer here, or you may want to apply something like Fourier features, calendar features, whatever. So you can find out about that in the transformations tutorial for forecasting if you're interested in that. Now, finally, in this round trip on probabilistic forecastings and composition methodology, if you want to roll your own forecaster, your own probabilistic forecaster, you can, of course, contribute one to sktime if you're interested. You can use it in your own closed code base in an interface compatible fashion. That's the primary use case of this check estimator utility, which you can use in a second or third party code base to ensure that your forecaster is interface compatible. And if you want to create a probabilistic forecaster, it will automatically check for compatibility for API conformance of the probabilistic prediction methods as well. If you have a public package and you want to distribute via the package sktime compatible forecasters, so we had a number of cases as well, we can also list it in the sktime estimator search, which will also lead to a listing in the on the web page on the search GUI as well as in all estimators. There's a pattern for that also in the developer guide. Check estimator primarily for use in continuous integration tests for your own estimator in a separate code base, or code base separate from sktime. If you contribute an estimator to sktime, then the CI of sktime will automatically run the tests, so you don't need to set up extra tests except tests specific to your estimator. So here's an example how you would actually run this. So let's say I've implemented a forecaster. If it's naive forecaster, well, this already exists, but let's say you write your own class use the extension template, fill everything in, you run check estimator on it, and that returns the results of all the tests. So it collects all the interface specific, so interface conformance tests. It of course will not test that your forecaster does something sensible, it will only test that your interface conformant. Okay. So any questions about that? Feel free to ask me, consult the extension guide. Summarizing, unified API for probabilistic forecasting and probabilistic metrics, predict interval, predict quantiles, and so on. So every probabilistic forecaster in sktime has these in the same, gives you the same output for the same type of output for the same type of input. Integrate seamlessly with other packages. So we've seen stats models, AutoArima, Prophet, or the newer deep learning foundation model-based forecasters. Some of them produce probabilistic outputs. Dependencies are managed on estimator level, so you don't need to install the dependencies unless you want to use the estimator in sktime. Composite model building is also very similar to probabilistic or not. There are some specific aspects that we have gone through today for probabilistic prediction, and sktime is easily extensible across the ecosystem. So, questions before we move on? All right.
Franz, just a note, we have an hour and 7 minutes to go.
Yeah, so I would suggest 7-minute break,
Yep.
and then we continue with cutting edge stuff for probabilistic forecasting.
People, if you run away after the break, you won't get access to the cutting edge stuff. Okay?
Oh, well, you have it on the repository.
We will delete it from the repo.
And it's also raining outside. So we start at the hour.
Do you want me to grab some snacks if there's snacks?
Oh, there's snacks outside?
If there are. Do you want
You don't know whether there's snacks outside.
Somebody said they got plums from outside, so I'm
Okay.
So there's dinner or snacks?
Okay.
Well, I just leave my stuff here. I just leave my stuff here.
Yeah.
Nobody write any faulty code, please. And I'm going to see it on the video. If someone pushes directly to the SciPy main branch and uses the version package I will tried out the ADI-CV clusterer? Have you tried out the ADI-CV clusterer?
Not yet.
It was added by one of our mentees this summer,
Okay, that's cool.
Schlock.
Yeah, no, I'm looking forward to it.
Yeah, we're doing Google Summer of Code, and we have lots of contributors now.
That's great. So you mentioned darts earlier. I've looked at darts a little bit. How would you separate sktime and darts? Like
So Darts is one of the few packages who are serious about a unified interface. I think they focus on performant re-implementations, which narrows their scope, but which makes these specific implementations, of course, performant. What it's lacking, extensibility, the ecosystem interoperability. So they are consultancy, and I don't think they have the dependency management layer the same way. They don't have composition, so pipelines reduction as much as sktime does. Maybe at some point they will. We have an adapter to Darts now. Yeah, philosophy-wise, openness, neutrality. You could argue sktime, because it's not a single commercial entity, and it's less prone to things like, well, we turn Red Hat or we turn Slack, if you know what I mean, or we turn Anaconda.
I've been very impressed with what I've seen so far. I like how it fits nicely with what I already know about sklearn.
Yeah, so interoperability is a key design part. And there was actually a point in the history where we were thinking about, so should we go down the road, and so sklearn is also, in a sense, closed but extensible. So closed in terms of which algorithms are in the main library, but they give people extension templates. And we go one step further, because we thought, so it was of course a heated discussion, but we thought the time series ecosystem is so fragmented. There are at least right now 5 larger libraries or companies who have their ecosystems. The data container types are inconsistent. So if we build just one more library that doesn't integrate with anything, then what do we add? Of course, there's a downside to it. So the more you focus on integration, it draws away from optimizing the interoperation. So if everything sits in one bucket and you don't talk to anyone else, of course you can optimize interoperation between the parts you own, because you don't care about anything else outside. So I think that's the main trade-off if you compare it with darts or cats.
So unrelated question. Have you met Rob Hyndman?
I have met Rob Hyndman, and in fact I have met him last week at the International Symposium for Forecasting in Dijon. Why? So I know, of course, Fable, I know Forecast. In parts, these have been also great inspirations. In parts, we are, some senses, departing, design-wise. And R is functional, so you have tidy. In R, you need to be tidy.
I don't like R personally, but I've got a lot of respect for it.
I will refrain from making a statement because I know people are watching.
Fair enough.
And I maybe want to go to International Symposium on Forecasting 2025 as well.
I guess for anyone listening, R certainly has its place.
So in some cases, by the way, more innovative algorithms get first implemented in R. It's closer to the research community. It's very difficult to convince some academics, oh, can you please implement your algorithm in Python? Look, here's a nice extension template. You only need to fill in the gaps. And no, I want to implement it in R.
Yeah.
But it's like there are like times we use bootstrapping algorithms implemented in R, but I haven't seen any in Python that's using bootstrap.
Yeah, that makes sense. Do you see, so with the work being done in like the transformer space, are you seeing that be done
So you mean
more?
transformers as in deep learning transformers?
Yeah,
Or- okay.
So, but specifically with use for time series forecasting, right?
Of course, we're seeing that,
Seeing a lot
and
more of that
we're
going
seeing
on than
we're
all
seeing the demand. Yeah, exactly. So now that's where R is starting to lose out. I mean, even in deep learning, right? They're basically using R bindings for the Python libraries. So
Different origin because now it's coming from Python, TensorFlow.
exactly.
And then which is all about Python used for.
So I've been at the symposium. There were streams in that where it's just not a thing. Just people will talk about their. Yeah, okay, people are watching. It was a very nice symposium. I enjoyed it wholeheartedly. Interesting people. Okay, now this sounds too ironic. I suppose I have already lost. Should we move on? Continue with notebook 5. So these are some. Yeah, so this is more of a collection of more recent developments, and at the start I would like to show you the distributions interface and then revisit how predictive distributions relate to things like quantile forecasts, interval forecasts. Then we move on to the relation of probabilistic forecasts to probabilistic tabular regression. So in the sktime ecosystem, there's also a package for tabular probabilistic regression. It's called skpro, and it's actually older than sktime, even if it's at the moment less popular. We have seen at the start reduction, so reduction to machine learning methods, and the same principle can be applied to reduce probabilistic forecasting to probabilistic tabular regression. I'm going to show that as well. And the third thing I'm going to show in this notebook is evaluation metrics, so deep dive in different types of evaluation metric. So quantile, interval, and distribution evaluation metrics. And any questions, please ask. So because this touches areas which are work in progress, it's of course less consolidated than, say, the previous notebook. Okay. So revisiting again the interval prediction or probabilistic forecast vignette. We've seen this a couple times. I think it's a good starting point after a break. Load data, specify the forecaster. This can be a grid search after adding conformal intervals in a pipeline and so on. Fit, predict, and then predict interval for probabilistic forecasts. So here's where we started. Predict interval, predict quantiles, predict variance we have seen. Now predict proba has remained a bit mysterious. If you remember, we printed the object there, and it was just this big box with stuff inside. So now I'm going to spend some more time on these probabilistic forecasts. And then I'll link back to prediction intervals, prediction quantiles, predictive variance. So what's this object that predict proba actually returns? It returns a distributional forecast, and that means you have, well, in the most general case, you have a correlated distribution across time points, variables, and potentially hierarchies. Most models, however, return these by marginals. So we have a univariate probability distribution per forecast index and variable and hierarchy level. So if you know, if you have used, what was the package? Forecast, Hindman's package that we previously mentioned. The return objects of similar kind in there as well, in R. Let's now construct the object. So I will now construct the object instead of getting it from predict proba to show you what it's actually like. So I construct it from scratch, but probabilistic forecasters do it internally. And we construct a smaller one so we can play around with it in the notebook. So what we're constructing here is a normal distribution, and you see it's not from sktime but from skpro. So skpro distributions are a bit ahead in terms of development, and we want to refactor it that it's only in one location. It's a normal distribution. It follows two interfaces, pandas, a pandas-like interface with row and column index, and the scikit-learn-like interface with get params and construction parameters upon construction. So we pass index and columns, like in pandas, and we have mu's and sigmas, some means, and standard deviations. So we pass a 2D array-like. This is a 2D array-like, so we get a 2D object if we pass these. And if I just print the object, it looks funny like this. So two ways to approach it would be to call functions, properties of this object. So I could do now something like get the mean, and that will be, oops, it's not defined, so I haven't actually run it, so this will be a 2D object. With the means, of course, the mu is the mean here. Could call variance on it. This looks just like in pandas. I could also do log and ilog. I'm not going to do this here in the interest of time. It has a plotting function for illustration, so it's less used for composition in algorithms, but it's quite nice for presentations like this, where we here see, okay, so here it's actually a time index on the left, but it doesn't need to be a time index. On the left, it doesn't need to be time ordered. So we have here the plotted probability density function. Can you raise your hand if you know what the probability density function is? That's what I thought, and that's why I'm going to explain it. So the idea is, this is a function that tells you where the event will happen in a certain way. So if you take, say, two values a and b, let's say we're interested in how likely is it that the value in March 1960 will be between 200 and 400. And to get the answer to that, we just look at the area under this curve between 200 and 400, and that's my probability. Of course, the entire area integrates up to 1, so 100%. So it's 100% that it will be somewhere. But the area between 200 and 400 is, well, the probability for the value to land there. So what we see here, so it's not true, it's not universally true where this function is highest. That's where it's more likely around it. It's only true if you have a single peak like this. The integration gives you a more reliable statement of where it is. So if you go through a statistics 101 or 201 course, then you see how you can interpret these functions as statements on the uncertainty, not just on the uncertainty as a quantity, how uncertain is it, but where is it actually going to end up. So key, another way to think about it, so this distribution, by the way, also has a sample method. So let's say I've talked about plausible futures. So if I sample 100 plausible futures, each time I do this, I get a value, and now I can pretend this is reality, but it's not reality, it's actually the predictive distribution. But if I would pretend this is reality, and each time I sample, then in the limit of doing this very, very often, the probability of seeing a value between 200 and 400 is almost exactly the integral here. So it's also an intuitive way to think about this. And the distribution encodes this information. So a distribution, what we are seeing here is a prediction coming from an algorithm that predicts not just, okay, between 200 and 400, what's the percentage, but in fact it predicts it for every possible interval I can come up with. So this is strictly a more richer representation of the uncertainty than just lower and upper bounds for a selection of intervals. This actually tells me for all intervals, for all possible intervals, what the algorithm thinks as a probability. It's a symbolic, or it's an explicit representation, if you will. So another, so you call these distribution defining functions. Again, for illustration, what a distributional prediction is the CDF, cumulative distribution function. You can also plot it, and this is closely related to quantiles. What does this tell me? If I look here on the x-axis, the y value above it tells me what does the algorithm think is the probability of the value being less or equal. So for instance here, if we look at March 1960, this corresponds to a prediction which on average is going to assume a higher value than the prediction from January 1960. If I look here at the 300, so in March 1960, so I mean these are made up numbers of course, but just for the sake of understanding the plot, it's thinking that about 50% and 50% of possible plausible futures, I will be less than 300, and in 50% I will be above that. And it's the same information as in the PDFs, but again it's presented differently. The PPF percent point function, it's the inverse CDF, it presents again the same information, but here you can already see how it relates to quantiles and why it's called the quantile function, because that tells me if I give you the quantile, the percentile, 0.4, 40%, it gives me the value below which that percentage of plausible values in plausible futures will lie. So 40% of the value observed in plausible futures, we have to go above 40% and left, and we get something closer to 200 than to 400. So any questions about these functions? These are symbolically represented by the distribution object. I can plot it, and of course I can also compute them by doing n.ppf. I'm going to show that in a moment. Any questions? Yeah, there's a question there.
Does the distribution function, or the distribution object rather, contain all those values within it, or is it generating those numbers each time you do like?
So the question is, does the distribution object contain those functions as stored objects, or does it compute them on demand? The answer is it computes them when you ask them for it. So it has, so in most cases, these are actually light interfaces around SciPy, not for all the functions, but SciPy already has, I mean, we're at the SciPy conference, so it already has, I think about 100 or at least multiple dozens of distributions already implemented very efficiently with NumPy, input-output bindings. What these distributions do, they are light wrapper for the purpose of symbolic representation. That's something you can't do with SciPy. So you have means and sigma. To SciPy, you have to pass mean and sigma, but here the means and sigmas are parameters of the return object. And if you call PDF or PPF, I can show that. So you do something like this. n.ppf at 0.5 gives me a here in the 3x1 matrix or data frame with the index and the column. That is computed on the fly. So not all the values, it's not It's not like 1,000 linspace and then the evaluates. It is actually the algorithm to compute these functions. And that is quite useful because you often need these algorithms if you want to switch between the probabilistic prediction modes, or you want to do some computations like, the continuous rank probability score, which is one of the metrics, please compute that. So many of the metrics, they need these. So if you think about the logarithmic loss, so who knows what the logarithmic loss is for a distributional prediction? Log loss for fitting a probabilistic neural network. I can show that later, but it's basically taking, so what's the logarithmic loss? If we take this prediction, so we take the PDF, evaluate it at the actuals, and then minus the logarithm of that. That's the logarithmic loss. So we actually need access to these functions as the algorithm, as opposed to pre-computed values, in order to be able to compute many of these metrics. That's an interesting point. Maybe I'll do it as a slight detour. So before we go there, let's link the distribution object to the different prediction modes. Okay? So predict var, so assuming they're all consistent with each other, I've mentioned previously these prediction modes are not necessarily consistent with each other. If they are, then predict var will return what the distribution returns and the variance of it. Okay, in the case of normal distribution, this is the standard deviation squared. Predict quantiles is the same, so up to reordering of how you present it is the same as PDF evaluates. So if you evaluate, for instance, the PPF, which is the inverse CDF at 0.1, that's the same number. Right? So it is, what number is this? It is the value below which 10% of values of all plausible futures will lie. 0.5, it's the value below which 50% of plausible futures will lie, so it's like the 50% middle scenario. So we see here this is actually the mean. That's the case because we are looking at the normal distribution, or more general, the mean of the distribution is the same as the median. So this is asking for the median of the distribution, in other words. And here we have the same for 90%. And if you just reorder them into the predict quantiles format, which is helpfully also possible using the quantile method of the distribution, we get the same table. Again, if the predict distribution would be consistent with the predict quantiles. So there's a side lesson here as well. So predict proba is the strictly richest of the prediction modes. You can actually get all the other prediction modes from predict proba if you wanted to, and if everything is consistent with each other. It's not necessarily computationally efficient if multiple of these are implemented, but conceptually this is how they are related. So predict interval, it's an interesting story. So what we do there is, if we want 70% nominal coverage, we pick quantiles that are symmetric around that. So we have symmetric nominal prediction intervals. So we have, so 70% coverage is 30% are not covered, 30% half is we have left, 15% not covered, and right, 15% not covered. So the quantiles that we need is 85% and 15%. Okay? I'm going to repeat this for 60% coverage at symmetric, so symmetric nominal prediction intervals at symmetric prediction intervals at 60% nominal coverage. 60% covered between higher and lower is 40% not covered. And if we have symmetric, then it's 20% on the left and 20% on the right. So we get 80% and 20%. Okay? And that's how these prediction modes all relate. Of course, predict interval, predict quantiles gives you a pandas data frame, which is more standard and nicer to handle if that's all you need than this distribution interface. Okay? So why the distribution interface? Then you might ask, well, I've already mentioned some things like the logarithmic loss, things like the continuous rank probability score. To compute these, you actually need access to properties and functions of the distribution. So some of the losses for probabilistic predictions you can only compute if you have specific methods of the distribution available directly. Or, well, you may have to store that stuff somewhere around, or that's then you need to know that in advance, which means it's not going to be as accurate, or it will have other problems interface-wise. So for statistics experts, if you are in the room, so the dependence, there can be dependence across time points and variables. Most methods and distributions implemented at the moment are by default marginal. So there's no dependence in, if you sample, for instance, between adjacent time points. That's a significant restriction, but for evaluating the performance metrics, that's enough. Distributions can also be non-continuous and non-parametric. So we talked about Monte Carlo sampling at the start. It will produce empirical distributions, not parametric distributions, unless, of course, you do stuff like variational Bayes. So under the same interface, you have empirical distributions, and you have the dot quantile and the dot PDF and everything here present. skpro, that's the sister or a companion package to sktime, which, well, the scope is distribution objects, but also probabilistic predictions. It meshes with sktime. It's the same basic interface principles, including shared base classes. There are symbolic representations of array distributions, which most of which, not all of which, are built on SciPy distributions. And of course, there are methods that SciPy distributions do not provide. For instance, for the continuous rank probability score, which are added here or estimated here. So these are, I think this is just a fourth of the distributions that SciPy provides, but it provides an interface where the parameters are actually parameters of the constructor, so it behaves like a data class, as opposed to you pass the parameters to the PDF or the PPF, and it is composable with the sklearn interface. So you have an interface that's sklearn and pandas-like, which SciPy does not provide, but in, I would say, maybe 70–80% of the distributions, you have light wrappers around SciPy for most of the methods. And these are probably the distributions that cover much of what's all going on if you want to do so a forecast, which is centered around a large value, or a forecast of a count. So count forecast, waiting time forecast if you have things like intermittent or slow-moving goods, intermittent events, time to event distributions in here. All right, any questions about the distributions, about distribution defined? So there's a longer tutorial, of course, of distributions in skpro. This is not the focus today, just wanted to show the key points for use as part of probabilistic forecasts. What is a distributional forecast, and how is it related to the forecast modalities that we have previously seen? Questions? Okay, so now let's see how this connects with metrics. So the three types of forecasts, I'm silently omitting variance forecasts. So there are three types of forecasts that we will look at: interval, quantile, and probabilistic forecasts. Base vignette, I think I don't need to repeat it, you have seen it 100 times already today. And we're now making the forecasts from these functions. The metrics can be classified by the type of forecast they compare with the ground truth. So if you make a distributional prediction, you can compare it with the actuals, or you make a quantile prediction, you can compare it with an actual. If you're making a distribution prediction and all your metric is the quantile predictions, in principle you can still use the distribution. So a number of common probabilistic metrics. So we have, I think, already mentioned today the empirical coverage. So that's different from nominal coverage. Nominal is the algorithm says it's going to be in this interval 80% of the time. Empirical is how often is it actually in the interval. So if you're producing 90%, so nominal 90% prediction intervals, and empirically you actually have only 70% or 20%, then maybe the algorithm wasn't that great at making a forecast. And there it already becomes a bit subtle in being careful about that these statements from the algorithm in 95% of the cases, these are statements coming from an algorithm, and in evaluation you should also be looking at the metrics that try to validate these statements. So you have also calibration, I'm going to explain that in a moment, continuous rank probability score, constraint violation, how often is the observed value outside the interval. Again, if you're producing nominal 70% coverage intervals, then this should be around 30%. Or you have, or your nominal coverage was inaccurate. Logarithmic loss, we've seen pinball loss for quantile forecasts. So by the way, this all objects is the same as all estimators, but in SK Pro, it's called all objects, and you can return tags in the table. And here your tag of SciType ypred tells you what kind of prediction it is actually for. So is it for a distributional prediction? There you have pred proba, or is it for an interval prediction, or is it for a quantile prediction? So this doesn't impact what we have seen before. If you do tuning, if you do evaluation, you pass the metric to evaluate, then the method inside knows, oh, I have to call predict interval, or I have to call predict proba, and then plug it into the metric. So how it works, probabilistic predictions, you plug them in. So first the ground truth, then the prediction, same as in sklearn. If you want by time index, if you want by prediction index, it's evaluate by index. Any questions about how to use the metrics? So because it was a question, I am also going to quickly look at the logarithmic loss. So we do this, so we can do this. Yeah, I'm not sure if this is actually in the just going to make these predictions again. So I have everything here. So now logarithmic loss, and I'm going to show you explicitly what it is. Okay, so is it hearing me because it's plotting log score, but that's not actually the name of it. That's funny. This is, and then we do this, and then we do, yeah, okay. Ypred proba. So let's do evaluate, dot evaluate by index. Okay, so now we have ytest and we have ypred proba. What we could also do is ypred proba And then we do the PDF at ytest. Whoops. What's going wrong here?
Should we expect white test to be a data frame?
Oh yeah, it does expect ytest to be a data frame. We should probably add some coercion here. Oh, where did it go? pd.dataframe. Just to be sure, let's do columns equals. Is it passengers? No, it's not passengers.
That was the suggestion.
Yeah, I know but it's the same as ypred proba columns. Okay, so now it's giving me this here. So now I have evaluated my PDF probability density function. You remember these at the actuals, and what we're now going to do is, I think we need numpy for that. And then we do minus numpy log. Which logarithm is it going to be? Let's see. Yeah, so these are the same. This is the logarithmic loss. So strictly proper scoring rule. So if it's minimized, then you're making the perfect prediction. And what you see here is you need the PDF to compute this metric. So what the metric does inside here, this evaluate by index, it does this. But in order to do this, you need access to the PDF. So if you look at the metric, in fact, it's a one-liner basically, which does this. But this is only a one-liner if you have a unified distribution interface with a .pdf. Clear? Okay, moving on, some useful plots. So something you might want to look at, so you know cross plots, and here the red bars are the intervals predicted. Blue is the middle of the prediction, so I think it's the median prediction. Green is the actual. So what nominal coverage did we want? It's 12 points, and we have 2 outside. It's about right, I suppose. Then quantile calibration, what does this do? So it applies the CDF to the actuals, and if you apply the CDF to the actuals, then there's a perfect prediction, it should be uniform. If you then order the CDF evaluates and plot them, it should be close to a line. So this is a diagnostic visualization of, or related to the metric, which here is called area under the calibration curve, or actually the area between the diagonal and the calibration of the probabilistic prediction.
Same function as a QQ plot.
Yep. This is a QQ plot, but CDF evaluates of the prediction on yeah, exactly. So it's a predictive QQ plot, which for some reason is called differently if it's applied to forecasting. So a minor developer note, most metrics actually exist in sktime and skpro. The reason for that is that, so skpro started out as a probabilistic prediction for tabular regression package. sktime then overtook it in development. So we just copy-pasted some stuff there because there it would become more robust. Now skpro has been upgraded to version 2, and there's now a refactor ongoing, which is moving stuff into a single place. The current state is things exist in 2 places. It shouldn't matter where you pick it from, but currently the skpro metrics are ahead of the sktime metrics. You still can use them, or should be able to use them exchangeably. There's no guarantee for that. maybe in a couple of monthly cycles that will be resolved, but just as a warning if currently you're doing any developer work or you're adding your own metrics. Okay, any questions about metrics? So these plots, by the way, or the quantitative statements corresponding to them, they're a means of quantifying the uncertainty and also a means of quantifying the accuracy of uncertainty predictions. So there's two layers here. There's first the uncertainty that the algorithm produces, tells you 80% of plausible futures, the value will be in here. But then you also evaluate the algorithm as to how accurate was my algorithm in doing that. And so you have the prediction, the probabilistic prediction of the algorithm. You have the metric that compares probabilistic prediction and the actuals. And on top of that, you have evaluation on backtesting, which gives you a statement of uncertainty about the accuracy statement. So evaluate, metric, predict interval, that's how things mesh together. And of course, in predict proba, you have a distribution that goes into distribution metrics. Okay, so last topic for today. I think we're almost at the end, and this is also somewhat work in progress. I will point out at the end as well areas where you can contribute if you want. So among the popular packages for uncertainty quantification or making uncertainty prediction, you have things like MAPI, NGBoost, cyclic boosting, and these are different packages with divergent interfaces, but let's say you want to use these for forecasting. So it's actually a popular request, oh, I want to use these for forecasting. Now, thing is, these aren't actually forecasters. So they are tabular regressors, so tabular probabilistic regressors. If you think back to the very start, so iris data set, petal length, petal width, and you predict a y from an x, and here what you get is a range for a y for a continuous outcome from these algorithms, but the x is in no particular temporal order, so they're the vanilla versions of these are not forecasting algorithms. What we still can do, of course, is we can do this. And the forecast here, instead of so the y hat, it's going to be a distribution or a predict interval. Now, where things were missing, of course, in the picture here is doing this. In sklearn, it's not going to give you a predict proba. Because sklearn for regressors, it doesn't have predict proba, it doesn't have predict interval, and that's where skpro, again, same philosophy as sktime, comes in. Probability distribution objects we've already seen, but the main thing actually is about tabular probabilistic regression. So you predict y from x, like in scikit-learn, not in any particular temporal order. It fills the interface gap for probabilistic regressors that we need in the bottom left. And since once we have this, we can use this in forecasters, just like make reduction, just like direct tabular regressor from the start, but now with a probabilistic forecast. So clear what we're doing here. We want to do forecast, the big robot. We want these y hats to be predict proba or predict interval objects. We want to do this by doing this tabularization and then applying the small robot, which is a regressor. But the regressor is actually a probabilistic regressor like NGBoost, MAPI, cyclic boosting, or jackknife after bootstrap, which is also a popular method.
I think it's available in maybe.
Jackknife after bootstrap.
I think so.
Okay, I also re-implemented it in skpro. So I thought maybe has ENBPI variants.
It does. And also
Oh, but jackknife after bootstrap is the old ENBPI. Yeah. So well, you might have multiple implementation of the same thing, but that shouldn't disturb you. That's better than having no implementation of the same thing. So, back to the bootstrap, but now it's the IID bootstrap. So in skpro we can do things like this. So this is the diabetes data set. It's a tabular data set. So you have features, 10 features, 1 target, 300 of 442 samples, depending on whether it's I can't read this table. So it's a tabular data set in any case. And this is now an example, the bootstrap regressor, so we don't have to install any extra packages. Principle is the same. You could put ngboost regressor here. That's an interface to ngboost. It's a third-party dependency. Or you could put mappy regressor here. And it wraps a linear regressor. So that's now a tabular regressor from sklearn. So what this does, it produces a probabilistic tabular regressor from a tabular regressor that's not probabilistic. And there's many methods like that out there, and there's many methods like that in skpro, where we collect them as third-party interfaces because they're kind of popular. And how it works is exactly the same like sklearn in the fit, and it works like sktime in the predict proba predict interval. So it's the missing link now that we have to do the make reduction that we need for the probabilistic forecast. The return objects, so here we do on the diabetes data set, we get the distribution. This is now an empirical distribution. You can almost see it because it does this, like a little staircase. So these are now not time points here for the CDF. These are just the indices, the instance indices in the test data set, and the target is called target. So these are not in no particular order. There's no temporal order here, but the same interface still applies. You can get prediction intervals in the exactly the same interface. So of course we want exactly the same interface because then we later want to stick it into an sktime reduction algorithm for forecasting. Of course you can use it on your own. There's a long tutorial about skpro itself in skpro. It has extension templates and everything. Okay, so there's some formatting. Okay, so this is just slipped over. So, if you use this in forecasting, there's 2 reduction steps here. The 2 reduction steps are, that's weird, some display issue. So you see this is bleeding edge. There's already some formatting issues. Number 1 and number 2, nothing. So the 2 reduction steps are, first we add the probabilistic mode to an sklearn regressor, which doesn't have the probabilistic mode. And then we use the tabular regressor, and we add a temporal dimension to it by doing this here, the tabularization. Okay, so if we use the bootstrap regressor inside, and then stick it into the make reduction, we get an sktime forecaster. And for that we can use the direct tabular regression forecaster. So that's one way we can do. We use an IID bootstrap on a tabular regressor to get a probabilistic tabular regressor, and then we do reduction to get a forecaster. So we do bootstrap first and reduction next. Reduction from forecasting next. Or we can do reduction first and do bootstrap next with a temporal bootstrap. So,
Even it says to compare the performance.
yeah, I know. It would be a nice research project. Yeah, if someone just gives us a compute cluster for that, to run it on the M4 and M5. Someone has a compute cluster standing around? So, of course, I'm saying these are things you can do, but I will, of course, say at the end which order of things it might be sensible to try, or what assumptions. So just showing that this then gives you now a probabilistic forecast. So we stick the skpro regressor, and this doesn't need to be the bootstrap regressor, it could be the MAPI, it could be njboost that we stick in here, and it gives you a probabilistic forecast, a prediction interval forecast, for instance, in this case. Or you can combine it with more complex pipeline constructs, like here's an example. So y from x, that's a compositor which you use in pipelines where you first generate features. And then from those features, this can be lagged variables of y, or this could be features from exogenous data, or it could be features like Fourier features, date time features. So I'm just, for the sake of it, constructing a common pipeline that you might find. So we have Fourier features, and we have a lag of 1. So a very simple pipeline which doesn't get exogenous data in the first place, but we use the endogenous data with a lag of 1. And so we also add it to the exogenous data, as it looks like. So we use a lag of 1, and this is chained with y. So we use y with a lag of 1 to predict y, and we use Fourier features, and we use the skpro probabilistic tabular regressor for that prediction here. So this double times is chaining the exogenous feature here. So the exogenous features are lag 1 and Fourier features. And here we fit and predict, and we get a predict proba. We have a predict proba. So if we would use any forecasters, we wouldn't have a predict proba. But we used the bootstrap regressor, which is bootstrap linear regression, just for it to be fast, but you could stuff a random forest in there if you want, or njboost. We have a predict proba. There you go. So, of course, this is one example. Integration is work in progress. Wish lists and user feedback is appreciated, so it's very bleeding edge. If you build a different pipeline, there might be a bug that you find. But I hope this outlines a bit how the building blocks are intended to mesh together. Join us on the Discord if you want to contribute. Now wrapping up, so we have now seen a lot of things. So a lot of things, you could do this, you could do that, you could do temporal bootstrap, and then use it for getting intervals. You could use a proba adder, which does not use temporal bootstrap. You could reduce, to tabular regression, or you reduce probabilistic forecasting to probabilistic tabular regression, which in turn you reduce to non-probabilistic regression. You can do all of these things. Now what is best? So you already said Sankalp, and I think you have not seen these slides. It would be nice to have a large-scale benchmarking study on that, actually. But even then, on your specific data set, there will be no universally best method, there is no free lunch, and so on. For practical applications, my recommendation tends to be the same. Instead of starting with a method that you think you need to try, start with a fair evaluation setup that is uncontaminated as well. So if you do method development on your data, make sure you have data that you don't use for method development to evaluate your algorithm. Make sure you agree on KPIs at the start. How do you evaluate? What's your evaluation setup? If you have business stakeholders, talk to them what their KPIs are. Of course, come up with empirically validable, quantitative, checkable ways to measure whether you have succeeded. Make sure you have baselines in there. Make sure you know when you're better than baselines. If you look at the M4X competition, they have not called it that way, but they also have made use of reduction. So if you say using machine learning methods, and of course you tabularize your data in a certain way. And so I haven't done the homework to actually try to write this up now with all the components we have. But the story here is that Of course, there's many more scikit-learn estimators out there, of course in scikit-learn, but sklearn compatible estimators than, for instance, forecasters that people have implemented. So if you use reduction, so reduction means using an algorithm for a certain problem to solve another problem, and the problem you reduce to is much more popular, you will have access to many more algorithms. For instance, tabular algorithms are more popular than algorithms for more obscure or more complicated to model tasks. The other part of the story, so of course we've talked about resampling, bootstrapping. Many of these methods, most of them actually, they implicitly or very explicitly assume or state you need some degree of stationarity, you shouldn't have seasonality in there. So unless a bootstrap method, unless a probabilistic wrapper says, oh, I can deal with seasonality, I can deal with trends, it can't. So assume in general they can't, which means you need to pipeline. We have seen in multiple instances how to deseasonalize, detrend, stationarize. You can see it also more in detail in the sktime pipelines tutorial, how to do that. Seasonality, stationarity tests, or custom statistical estimators for that. Deseasonalize, detrend, and detrend in particular, maybe detrend with exponential smoothing. That's a starting pipeline, and then start adding the proba stuff. Because if you do conformal intervals, you do bootstrapping on a time series like the airline dataset, which is not detrended, we've seen this, and I think I've signposted this as well earlier. It's not going to result in a good forecast. And we have seen this in the make reduction, where we've seen the histogram estimated couldn't extrapolate, and once we detrend it, it works fine. That's important. Don't forget about this, is my recommendation. Also, the wrappers or the reducers typically assume this. Temporal bootstraps typically assume this. Reductions in the IID space. So if you reduce to IID, then you assume exchangeability, which is closer, or which is more satisfied in a moral way if you've already stationarize your time series at the start. Then feature extraction can make a substantial difference. We've only really scratched the surface here. If you've been to the Temporian tutorial today, you've seen 4 hours of efficient feature extraction. You can, of course, combine Temporian as a component with the pipelines. We have a lot of onboard components and other integrations as well. There's a pipelines tutorial which doesn't happen today. Of course, if you happen to catch it, or you see us on YouTube, you watch us on YouTube, or join another presentation over the summer. Questions? Oh, easy to extend, of course. Stuff in development. So everything we've seen, you can add your own variant. You can add your own probability distribution, metrics, tabular regressors, forecasters, in a first, second, third-party code base. Code base doesn't need to be open. Check estimator works for all these objects. Test for interface conformance. It should be plug and play. If not, it's a bug. In the probabilistic space, bleeding edge stuff going on. If you want to contribute, we're very welcoming of new contributors. So just join our Discord. So I'll click this link. Community Discord, see what's going on. We have a large summer program with interns and mentees, some of them funded by Google Summer of Code. We welcome senior contributors as well. If you have time to contribute or work towards a specific feature, I've mentioned the refactor sktime, skpro, simulation interface for temporally dependent forecasts, then the distribution calibration stuff, hierarchical reconciliation, Bayesian models. Lots of stuff going on. So, hope to see you here, or tsbootstrap, I think, also has a roadmap, which you can access on the README page. Again, sktime is non-profit with a mission of providing algorithms for the general ecosystem. Integration, very unique in the sense of being of this integrative design philosophy, community philosophy. Packages, ecosystem working together. We're welcoming open community, already mentioned that, so here's the link to the Discord. There's a new contributors guide. You can follow us on LinkedIn and meet us at another conference or event. Questions? No questions. I've scared everyone to silence.
Okay, just a note, sktime is completely, like you mentioned, open source, non-profit, and do a lot of mentoring. If you go on tsbootstrap's homepage, there is a buy a coffee button. I'm completely for profit. I will take your money. Sktime is non-profit. I'm all
So
about
non-profit doesn't mean we don't take your money.
Yes, if they use it for the good of society, I will spend your money and myself.
Well,
Take it.
we reinvested in the maintenance of the code base and helping, running the mentoring program,
Absolutely.
helping out the ecosystem such as tsbootstrap.
I reinvest in buying myself beer.
Yeah, well, that's a reasonable reinvestment. What's the return on the investment, I wonder? Yes.
There are no metrics for it.
Depends on the definition. Yes. Well, at least no probabilistic ones. All right, I think that's the closing word.
Yep.
Buy Sankalp a beer.
1 minute to go. Vietnam.
Questions?
Oh, sure.
I should go in the picture for the.
I don't know.
Well, we're still on.
Right there? Okay. Oh, you know what? We can take this time to take a selfie with the whole group.
Oh, okay.
Oh, yeah, why not? Okay, I'm just
Really?
going to turn around.
I think you have to
Literally.
ask for permission if.
Guys, selfie? No selfie? Okay, all right. You can come in here. You can
All right,
selfie.
all right.
Okay. Please. Okay. Perfect. Thanks, y'all.
Thank you.
Yes.
Yeah, selfies. Modern nonsense.
Yeah, you think this is bad? Just wait till you meet Gen Z. My God. I've been chatting about I have a car. I'm gonna go to the Airbnb, pick it up. Hungry as shit. 3 other people interested in getting lunch.
All right, let's
at
get
whatever.
lunch.
And I've saved space for you.
It will be my lunch.
Sure. I will be back in like 20 minutes.
So I can join you or I cannot join you.
No, you can join. I've kept one space open for you.
All right. So we'll meet
So that
here.
fills up the car. Yep. I'll text you, and I'll meet you at the entrance.